So we are starting the afternoon session. We are starting for the afternoon session. We will have first Josh Greenley and then the EHT team crowd. And Josh is going to talk about Dash.
Okay, I'm going to give you a few examples of what I think are some interesting AstroStat questions. I guess I put some of them in the abstract that I gave to Vinny yesterday. So let me first, well, before getting started, if you haven't heard about Dash, go to that website. You can, actually, it is going to be also transformed into a new entry point for more public-oriented people, but this is the intro if you want to use the data. It's very easy to get at. And since I'm not going to talk about this otherwise, and I think some people may be interested, most of you know that we had a terrible flood here a year ago, right out there. That's what all that digging for the next 6 months was all about, to fix it. It flooded. The only place it flooded in the observatory was the basement of the plate stacks, where the plate scanner is, and where all of our computers are. We lost a lot of equipment. We had 61,000 plates underwater. Major disaster, a couple $1 million worth of damage. Fortunately, Harvard has insurance. It's all been covered. It was a huge amount of work to, fight off these, rather difficult insurance investigator types. But anyway, it's all been done. The plates are being cleaned and processed and coming back here from a facility up in North Andover, Mass. It turns out to be an international place to do flood recovery reparations. They'd never worked with glass plates before. These are 8 by 10 inch pieces of glass. 100-year-old plates, very, very valuable. But they are doing a fine job. They're using a process that we developed here at the Harvard, basically Preservation Center, which is a place that deals mostly with books and the like, but also with photographic materials. So that's the good news. It's all being not only dealt with, but it is nearly done. Another 6 months, all those plates will be back here. And then the final part of the update, just before getting going here, is the scanning got interrupted for a year. The scanner was destroyed, the old one. This is a major piece of equipment that I'm not going to talk about otherwise, but that was replaced a year ago. It took us another few months to make software adjustments and improvements on the whole system to accommodate this new upgraded scanner. That's all working. We are now scanning 500 plates a day, which is unbelievable. The goal for the project was 400 a day. If we'd been able to do that on day one, we would have been done 5 years ago. Needless to say, we couldn't do that on day one. We had to, enormous amount of software and hardware development. But it's all working, and we should be done in about 2 years. We're now about half done. 200. We had a little ceremony last week or the week before. Plate number 200,000 was scanned. And anyway, so 2.5 years it'll be done. Okay, on to what we're going to talk about here. Just why is this project of interest to us, and why should you be interested in looking at some interesting analysis questions? Well, these are just a few of the very many things that one could say about it. It's a 100-year database, the only one of its kind in the world. It's been used for the last 100 years or 120 years, but now it's all becoming digital, and that means we can look at time domain astrophysics questions that have very long time scales by definition. It also means you can look at very large amplitude flares, which I'm interested in, from blazars, from black holes in general. That was why I wanted to do this project. And you can look for otherwise very rare events. We don't know much about how frequently. I'm going to show you at the end a flare from OJ 287 that'll ring a bell with probably most of us here. That raises itself another interesting statistical question. If it's real, it's remarkable. It's a 1 hour flare of a 4 magnitude increase. in that object, which has never been seen in the modern data. But there is a catch, which you're going to see, and I think we can explain the catch, but we'll get to that. Okay, so these are just a few of the reasons, and just one other summary thing. I showed you this in a head talk last year, so apologies if you've seen it, but just this is the typical way to talk about the time domain landscape, some measure of luminosity, in this case absolute magnitudes, if you like those, versus variability timescales, and Dash covers a good fraction of this whole plane. When you hear or see that it's 100 years of data, that doesn't mean that there isn't access to 1 hour timescales. There is. I just told you about a very possible, very probable, I think, 1 hour flare, and that's because there wasn't just a single telescope banging away doing all these plates for 107 years. There were 80 different telescopes. It's incredible what these guys were doing here. I mean, the whole story is just remarkable. Read The Glass Universe if you haven't already for part of the story from Davis Sobel, who, by the way, will be here in a couple of weeks to give the CFA cloak-in. So the reason why you can cover short time scales is there were lots of telescopes, and it's amazing that even from one site, the two different or more than two telescopes, and probably this was by design, I'm not sure. One thing that isn't quite clear is how they organized this. You know, what is site A doing that site B is not doing, or vice versa. There was some organization, to be sure, but they were frequently, the telescopes were also, just one other note, not at all identical, ranging from what are basically camera lens size that were very wide field, short focal length lenses. So those gave 30-degree imaging of the sky, which means you could tile the sky very rapidly, to long focal length lenses on the back of, you know, what we regard as real telescopes, 8-inch up to 24-inch, that sort of diameter range that would be operating from the same site in some cases. So that's one reason why there was, you know, coverage on the hours to days time scale. The other is, and then I'll stop with all this intro stuff, they did multiple exposures. Plates, you know, shipping plates to Peru and South Africa in 1918, when you had to dodge German submarines in the Caribbean, which, by the way, you know, did wipe out at least one delivery of plates. They're down at the bottom of the Caribbean somewhere. Was not easy, so they were parsimonious, and they would take, not on every plate, but on many plates, multiple exposures. Our software can peel those apart because they're, you know, not of the same piece of sky. Sometimes, again, being not just parsimonious, but trying to be able to calibrate, they would make a sizable slew. These are small telescopes. That was easy enough to do, and go up to Polaris if they were in the northern hemisphere, well-established field of standards, and use standards they already knew or that they were using. So all of those things are dealt with, and that gives rise to a whole range of timescales. And just the last note is on that multiple exposure front, we have succeeded in doing iterative solutions that begin, believe it or not, in the very first pass with astrometry.net, which probably many have heard of, David Hogg's wonderful creation. And then all the higher order corrections to do arc-second astrometry on these plates with distortions and everything all taken out. You do that solution first, beginning with the brightest stars. You remove all those stars from your fit. You do it again, you get the next exposure, and so forth. We've done up to 5 exposures on one plate. These are all, you know, overlapping fields. So it does work, but it's not finished in the way that it's being implemented in the database. So there will be a lot more coverage than you can find now because all of those multiple exposures are not yet fully accessible in the database. But that will come. Okay, so let's get on with this. And let me show you one example of something that raises some interesting, or at least one interesting question. That is looking for transient outbursts of black hole X-ray binaries. I think probably most people here know that these things are all transient systems, every bloody one of them. They're not persistent sources. Some of them are on for long periods of time, just to give you the background lore. One of them, GRS 1915, appeared out of nowhere in 1992 and has been on ever since, just bouncing all over the place, doing crazy things, and presumably, who knows when it'll disappear, right? But that's a very rare exception. The others are typically on for a month or so in a big outburst and then quiescent for long periods of time. So one of the motivations was to look for these things that we already know about, all of which have been discovered as X-ray transients. None have been discovered any other way. The whole 22 or 23 now dynamically confirmed black hole X-ray binaries were all found by producing X-ray transient outbursts, and to try to constrain the recurrence time, which tells you, or I'll very briefly go over this, how many systems you're missing. One has to try to look for historic outbursts. And just one last bit of history up until what we've been doing here, and there are a whole bunch of papers in progress here to summarize this, which I've waited on because I've been waiting for more coverage. Just that's my excuse. Here's an example of one of the known systems, which was discovered actually only about 15 years ago. It was quite an exciting discovery because it was the first one discovered in the galactic halo. What's a black hole low mass X-ray binary doing up in the halo, right? That's another interesting set of questions. Well, here it is. We found it back in 1928 with an optical outburst, which you can see there clearly enough. I'll show you the expanded view. But this shows you in one slide what I mentioned in the abstract. There's a 15-year gap here when Menzel, the director of the HCO, said, why are we doing this? I could, use that, whatever it was, a few hundred K a year to run all these telescopes, probably more than that, on other projects. And then Leo Goldberg, when he got here, said, no, this is important stuff. We're going to start up again. So there's that gap, which raises statistical questions that I'm actually not going to talk about. But there's an example of an outburst, and it's the only one I'm going to show you. There it is in more detail. So the question becomes, when I would see, or if we find an optical transient that looks like that, does that immediately point to it being a black hole system, or could it be something else? And the only way you will convince the community, or that will be convinced that it's a black hole, is to do all the hard slogging legwork of optical spectroscopy, measure a mass function, and demonstrate that the system contains a black hole. That's what we're doing, and that isn't going to be in this talk, because that's another major thing. I will talk about that later this year. But so here's the light curve blown up, and what I've mentioned here is that from looking at the duration of the outburst, which you can see in years here, was of order a month for a roughly 1 magnitude decline, which is typical of these things. There is missing coverage there, which doesn't tell us very much about the rise time of this flare. Unfortunately, there are other much less interesting, at least to me, binary systems, cataclysmic variables, white dwarfs secreting from very low mass companions, even lower mass typically than what these black hole LMXBs have, which are K-dwarf companions, so-called WZ Sagitti stars, which have very rare and therefore infrequent outbursts, usually not as infrequent as this. This is 1928. The system was discovered in 1900, so you can do the arithmetic. Nothing in between that we've found in the DASH data, which is the only resource to look at. But so the one question, which I will just mention and I won't have time to deal with otherwise, is can we do light curve or duration rejection a priori? Going after one of these guys, suppose this was not a known system. We have found other systems that in the optical, in their outbursts, look very similar to this. and we go after them, and it's a huge amount of work. They're very faint stars. This is MMT or Magellan. This is not small telescope stuff. And even doing that, sometimes, many times, the answers are ambiguous. It's a lot of work to demonstrate that you've got what we already know in this system, a real black hole system. So that itself is an interesting question, but let me show you why we care. In 30% of the coverage, and we're now up to 50%, so these numbers are being updated. There are 4 of these things out of the known roughly 20 for which we found the first historical outbursts. Okay, I'll speed up. And all of that leads to interesting population studies. Here's the statistical question I wanted to have people thinking about. If you're interested in measuring a duty cycle, what fraction of the time is the source on? This is equally relevant to AGN, by the way. In fact, the duty cycles from our very incomplete knowledge are probably actually quite similar, of order of 1% or maybe 0.1%. This is what we've done with these first 4. In yellow is marking the time for each of those 4 systems from the brightest to the faintest. You can see there's a lot less yellow down here in this guy, which is fainter and therefore has less coverage. And that is then being converted into estimates of what the duty cycle could be from each of those 4 systems and into a cumulative average from which you can read off in this right-hand plot here a 90% estimate of the duty cycle, 0.9 up there if you like that as a probability, is about 1.5%. Okay. Is there a better way to do this? When you have randomly taken data, random white space in between your data points, what's the optimum way to do this? So I invite any suggestions. So there isn't time to go through what this means, but the bottom line on one slide here is something remarkable. When we do something similar for neutron stars, we find that the populations that we infer must be there, given that we're only seeing 1% in round numbers of the black holes, could be 10 to, well, 8 or something of order 8 to 20 times larger black hole population of these low mass X-ray binaries than neutron stars. That's an incredible result because your intuition says, the IMF says there must be many more neutron star systems being produced, neutron stars being produced than stellar mass black holes. Well, that's not what these results so far are pointing to. Okay, AGN 3C273. Here the question I want to point out is, we've known since it was discovered on these plates, the old-fashioned way of looking through an eyepiece, to be a variable star. That was only 2 months after Martin Schmidt had published the discovery. Now we can do a lot more with the digitized data, but here's the question. Are we looking at individual flares, short duration flares, on top of what looks like a smooth, much longer time scale background variation? What's the best way to isolate flares? Okay, I'm just going to plant that question because we don't have time. And we can do power spectra, and that points to interesting things, a 16-year time scale that looks very significant. There's a suggestion of it that I mentioned down here from a 1999 paper that found basically the same number from VLBI data, so nothing to do with the optical, or is this just red noise? That's the big question. Finally, OJ287, which is highly variable. I mean, it's going all over the place here. Here it's a little frustrating that there isn't more coverage. I thought by now we would have more data points, and I'm really surprised that this region of the sky, for whatever reason, I'm still checking on this, doesn't have more coverage. But this is what we've got. There's the remarkable 4 magnitude flares in between that red data point and that red data point. There's only 1.5 hours difference in time. So is that real? Well, this is the flare of OJ287 with 3 field stars, a very shallow plate, one of these very wide field plates, so it doesn't go very deep. And that is a very real detection. It's within 2 arc seconds of OJ287, but there are plate defect images here. This is a rare occurrence on these old emulsions. This was 1918.93, a couple more digits, whatever the exact date was. So there are other, and as I say, infrequent examples of these plate defects. In fact, I gather the old days when people were developing the plates, they called these things that looked like stars Kodak stars. Blame it on Kodak. The emulsion was faulty, right? Usually you can recognize them by the PSF. And these look very round and look like typical Kodak stars. That doesn't look as round, so I think it's real. And doing the obvious things, astrometry says it's real, but how do you convince the world that that is indeed a remarkable flare, which I think is the largest thing that has ever been seen with the system. A very rare event, but we got 100 years of data, so we managed to catch it, even though there's relatively less coverage than there should be. Okay, so that's the example I wanted you to see, and why are we not advancing? Ooh. Oh, this is this god-awful Xfinity wireless thing that pops up if you don't turn your wireless off. Everybody's discovered that in here. There's the story used to be that there was a contractor out there who, I don't know what the reason is, but okay, I'll skip over this. This is just taking OJ287 and looking for the 11 or 12-year period. I guess it's on the next slide, just to show you, because this is an obvious question. Do we see the claimed Valtonen et al. Periodicity? The answer is not significantly. That's where it would be, 11.5 years. This is probably almost certainly a red noise peak at the far left again. So no evidence for quasi-periodicity here in this, whereas 273 looks more interesting. And since I'm out of time, let me just stop here then. This is a few examples that I've just gone through, and I'd be happy to discuss any of those. And if people have insights or thoughts on this, let me know. Okay.
Thank you, Josh.
Yes, Roseanne.
I have some very practical questions because
Yeah.
this is such a great data set.
Yeah.
At this point, what amount of it is available for us to use, either to just say, I don't know what I'm looking for, but I have some ideas, some
Yep.
codes I'd like to run to look for effects, and I'd just like to read in, the whole data set and
Yep.
see what happens when I try my
Reading
algorithm.
this is a data set that is not what other data sets are. It's an enormous data set already. If you want the numbers, it's about 400 terabytes at this point. It'll be a petabyte when we're done. The whole thing is organized as an object-oriented data set. So, and you can do cone searches and download, but that only buys you neighboring field stars or galaxies or whatever you're working on to compare, which is useful. So the example I showed you for OJ287, looking at that was a zoomed in image of just around this thing on a 30-degree chunk of sky. That was 5 arc minutes or something, those images I was showing you. So you have to really, to make use of the data, you really want to know what objects you want to look at. You can't easily interrogate it blindly.
I see. And what fraction of the sky is available right now?
So there are 12 data releases. We're scanning in galactic latitude. We have now nearly finished the 6th bin of 12, so we're very close to 50%.
That's
okay.
great.
And DR6, which will be the slice, or 15-degree slices in latitude, which is meaning we've done the largest chunk of sky, right down in the galactic plane now. That data release will come in November.
Fantastic.
So we're very close. And
Thank
that'll
you.
be half the sky is done. But right now you can go through DR5, which is 37% of the sky. And that's been out for a year.
More questions?
So, yeah.
How do you find the flares like in 287?
How do we find it? Just looking at that light curve.
So you
But
have to.
that's another question. What do you define as a flare? Is that what you're really asking? Yeah.
Well, sort of, but also, like, so your database contains light curve for a source. So
Yeah.
if I'm interested in particular source,
Yeah,
I would go and look at that source and then
Yeah.
plot the light curve.
exactly. Very easy to do. I could do it here in 10 seconds on the screen, but
Right.
that'll take time we don't have. But yeah, it's very fast. You can just literally, if it's a Simbad recognizable object name, you can just type in OJ287, and in 10 or 15 seconds, that light curve will appear with all the upper limits. If you can choose to plot the upper limits, you don't have to.
Right, so for this one is
So-
easier, but then you had this example of XT 1118, right?
Yeah.
The black hole candidate.
Yeah.
And you know that there is nothing, so you went.
So there you
and-
just go to the coordinates. The XTE name or whatever is generally not Simbad recognizable. So you type in the coordinates, J2000 coordinates, and the whole system will find all plates, which is, in that case, if I went back to that light curve, probably a couple thousand plates, a couple thousand data points over 100 years that you get to look for any evidence of an optical outburst. And given that the outburst for those systems, that one included, typically last a month or two, you've got a very good chance of finding it. And that's what those duty cycle numbers are all about. So,
Thank you.
okay?
Thank you very much, Josh. Very impressive. So we are moving on to the next speaker, first one of the
Yep,
EHT team, and
there you are.
it will be Michael Johnson.
That's 8 minutes in, or?
Will be 13,
Oh,
11 minutes. Yeah.
okay.
Do we see the black hole?
Okay, can everyone hear me okay? Not too loud. Great, well, I'm really delighted to kick this session off on sort of astrostatistics applications to the Event Horizon Telescope. And since I'm the first speaker, I'd like to give you just an introduction to what the EHT is. And then I'll dive into a specific problem on scattering mitigation, actually. But also because, it's an afternoon session, I thought it might be worthwhile to inject some whimsy. So to explain the EHT, I thought we could draw some inspiration from ducks. Here we have a bunch of ducks. They run, they jump into a pond, and they start kicking their feet furiously. And you'll notice that near the ducks, the water is stirred up and random. And then further away, you see these nice, smooth, outward propagating wavefronts. Okay, so this is actually it's a nice toy problem in statistics. You can model the ducks as basically generating a random process. Here we'll pretend like it's Gaussian. It may not be. And so the question I wanted to pose is, suppose that you're sitting around the boundary of the pond, and let's say that you're blindfolded. So all you can do is you can feel the water sloshing up and down. And let's suppose that you have a lot of friends all around the boundary of the pond. They can all take measurements of this sloshing water. The question is, what is the optimal way to tell where the ducks are in the pond? And is it even possible? So all you can do, you're blindfolded, you just feel the sloshing water, and you want to know where are the ducks in the pond that are kicking their feet. So to motivate this a bit more, here's a toy representation of the toy problem. On the left, we have a pond where the ducks are very close together, and on the right, the ducks are spread far apart. And so now we'll let them start splashing around. You see the waves propagating outward. Again, near the center, the water is stirred up and irregular, and by the boundary, it's these nice coherent wavefronts. And the key difference you'll notice is that on the left, you have this nice gentle sloshing pattern, so that if you and a partner were standing next to each other in a pond, you'd see basically the same pattern. But on the right, there's more interference between the different patterns, and so you see that the coherence length on the boundary is much shorter. So it turns out that if you want to know where the ducks are splashing, all of that statistical information is contained in the covariance function around the boundary of the pond. It's actually a sufficient statistic for the problem. And just knowing the amplitude that's sloshing at one place doesn't actually tell you much. It sort of tells you how many ducks there are in the pond, but it doesn't tell you where they are. It's only by comparing with your neighbors that you can start to piece together this information of how they're distributed in the pond. Now, this may sound a little silly, but it's actually very closely related to interferometry. And so what we're doing is we're looking at these distant astronomical sources, and instead of ducks, what we have is electrons that are gyrating around magnetic fields, and they're sending out these electromagnetic waves. And what we do is we space telescopes far apart from each other, and they're measuring the sloshing electromagnetic wave as a function of time. And each telescope by itself doesn't learn much. It just tells kind of how much emission is coming from the source. But the comparison between each pair of antennas is what's telling us about the picture of the source. And it's actually possible to piece together many different measurements in this interferometric way to get the image of the source. So the reason we do this is for angular resolution. So to put that in context, your eye has an angular resolution of about an arc minute. And the biggest radio telescopes in the world, these 100-meter monsters, have about the same angular resolution, about an arc minute. And this is because radio wavelengths are so much longer than optical wavelengths. Whereas optical telescopes, of course, are much larger than your eye, and they can get down to something like 50 milliarcseconds. Now, the magic of interferometry is that it doesn't matter how big your dishes are, it just matters how far apart you can space them. And so that determines your resolution. And the price that you pay is that we're not making a picture directly anymore. We're not just snapping a photograph of our sources. It turns out that each pair of telescopes is measuring that one covariance element, and that covariance element is exactly given by one Fourier component of the image on the sky. And so what we have is this sparse set of Fourier elements of our image, and we have to somehow come up with algorithms that turn those into pictures. And Katie will talk about more about that in a moment. So to summarize, the Event Horizon Telescope is not one telescope, it's a set of them all over the world, and we're equipping them with the necessary machinery to do VLBI. And so when it's done, this entire VLBI network will have an angular resolution of about 20 micro-arcseconds. So this is thousands of times better than Hubble. The reason we're so excited about this is that here's a simulated image of the galactic center. And what we expect to see there is a bright ring of emission. And that's photons that are lensed near the horizon. So the diameter of that ring should be about 5 times the Schwarzschild radius of the black hole. And the final resolution of the EHT is going to be about 20 micro-arcseconds. So, if it all works, then we should be able to resolve these sorts of features. The reason that it's such an exciting time for the EHT is that this past April, we had our first run with a full array. So this is the first time ever this year that we've had enough sites that we might be able to actually make pictures. So I can't show you those pictures today. Data processing is ongoing, but it is a great time, and I think that there's a lot of reason to be hopeful. So the specific problem that I wanted to dive into a bit more deeply is that interstellar scattering affects the EHT. And the interesting thing is that it affects the EHT in a way that no previous VLBI experiment has ever really had to worry about. It's because we're at such incredibly high angular resolutions. So it turns out that most of you probably know that the Earth's atmosphere causes optical light to be scattered. This is why stars twinkle if you go out and look at them at night. Okay, and it turns out that at radio wavelengths, the interstellar medium does the same thing. It's because the index of refraction depends on the density, and so because it's turbulent, you have these density inhomogeneities that are causing the light to be scattered as it's propagating towards us. So the first point is that this is intrinsically a stochastic effect that we're trying to understand. And this causes a lot of things. It causes our images to be blurred out, and it also causes them to become speckled, like in the optical case. So the real question for us is, how does scattering in the interstellar medium affect observations with the EHT? So here's just one example. This again is a simulated image of Sagittarius star, and here's how it would look like after being scattered at 400 gigahertz. Okay, now what I'm going to do is I'm just going to step down in frequency, and you can see how the scattering changes as you go to longer and longer wavelengths, or shorter or lower frequencies. So here we are at 85 gigahertz, and you can see all that intrinsic structure is washed out by the scattering. You can't study that horizon scale structure anymore. The reason this is important is 85 gigahertz is the highest frequency that VLBI was ever done before the EHT. So there's just no hope of studying what's happening on those horizon scales unless we can build arrays at shorter wavelengths. And then the next question is, what can we do about this scattering? because it still remains an effect for the EHT. So it turns out the scattering actually has two effects, and they're opposite. So one effect of the scattering is that it's blurring things out. It's masking the structure that's behind it. But the second effect, which was apparent in that movie and also in images like this behind the jet contrail, is that scattering is introducing its own substructure into the image. So even if you detect small-scale structure in your image, you still can't be sure that it's from the source. It might be from the scattering. So how do we deal with this? Well, it turns out that we can deal with this in a statistical framework where we decouple those two effects of scattering. So the blurring is from the really small scale stuff in the scattering screen. So this is on scales of something like 100 kilometers in the interstellar medium. It's microscopic scales. And so because they're happening on such small scales, we can approximate them by their ensemble average effect. And so then two things happen. First, as an ensemble average effect, it's deterministic, and that means that it's invertible. So we can get rid of that entire piece of the scattering, or at least replace it by something that's understood precisely. Now, in addition to that, the same scattering is introducing that substructure. It's not like a different type of scattering or a different scattering component. It's the same scattering material. And this comes about because of these large-scale modes in the scattering that's steering and distorting rays on their way to us. So what we have to do is we have to keep those in the prescription. So we say that there's one part of the scattering problem that's deterministic, and then we have to keep this stochastic part, but it's described by many fewer variables because it's only these very large-scale modes. Then what we do is we change our imaging so that instead of just taking a set of measurements and reconstructing an image, we take a set of measurements and we simultaneously reconstruct the unscattered image and the large-scale modes. So this little picture at the bottom just shows you, that on the left, that's how the image would look after the diffractive scattering, where it just blurs it out. On the right is the scattering screen, and as you slide that over the image, you can see it adds all those small-scale distortions. So the game here is to solve for them both at the same time, and we can do that because we understand the statistics of the scattering. So in Fourier space, the scattering is basically just a bunch of uncorrelated Gaussian random variables. And so we know the power spectrum, and we can regularize against that. Any image could be produced by any source plus scattering because the scattering is random. But we could say that certain images are very unlikely to be the intrinsic image, and certain types of scattering screens are very unlikely given its known power spectrum. So it's pretty straightforward to write down just a log posterior distribution for an imaging problem that involves any sort of priors you have about the unscattered image, and then a data log likelihood. The scattered image has to be compatible with the measurements that your instrument makes. And then in addition to that, we have this additional log prior on the scattering screen that says certain types of scattering action are incompatible with the power spectrum that we measure. So here's just a few examples. Here on the left, you can see a very simple example, an unscattered image that's just a ring, and then how it would appear after scattering. And then I'm showing 3 different image reconstruction techniques, assuming that you sampled it with a VLBI array at 85 gigahertz. So the first is just conventional VLBI imaging. There's no scattering mitigation at all, and so you do a pretty good job at estimating the scattered image. The second thing you could do is you could try to eliminate that blurring effect of scattering. So you could try to sort of de-blur your data. And that's easy to do because it's this deterministic process. But the problem is that in doing so, you're amplifying all the substructure that the scattering brought to the problem. You're ignoring those large-scale modes, and so you're actually making their effects worse. And so there you can see in the reconstructed image that you get too much compact structure. And then the last image is with this new technique where it's trying to sort of balance those two approaches, and you do a lot better at getting back the unscattered source. Now here's the same thing at EHT wavelengths, so 1.3 millimeters. And again, here the image before and after scattering, you can see the effects of scattering are much weaker. So there is hope of seeing features like the shadow, but the scattering is still kind of washing out some of those fine scale structures like around the photon ring. And again, with straightforward image reconstructions, you do a pretty good job of estimating the scattered image. If you try to just de-blur your data, but you don't account for those large scale modes, you get a little bit too much compact structure in your reconstructions. And then with the new approach, it tries to balance those out and does better at estimating the unscattered image. So this is encouraging. Even with a pretty sparse array, the EHT seems to have enough information that we can simultaneously be making images and mitigating the scattering. So just to summarize and maybe step back a bit, I think the EHT can really benefit from new approaches in astrostatistics. First of all, our data and our measurements are from these very well-defined statistical populations. We really understand the framework to describe these. The second is that it's comparatively small amounts of data, so we can really do the proper analysis. We don't have to cut corners. And then the last point that I think is really important is that the EHT has a lot of differences from standard VLBI. We have to worry about things like time-varying sources because we're at such high angular resolutions, and Katie will talk about this. We have to worry about scattering. No one has ever had to worry about this before. And our array is very different than standard VLBI arrays. So I think this is really kind of a rich discovery space. There are a lot of difficult problems that have never been faced, never been solved. And so it's a fun project to work on in that sense. Scattering in particular is fairly challenging to deal with because it has these two opposite effects. It's introducing blurring and it's also bringing its own substructure. But by approaching this as a statistical problem, we're able to solve it in a way that I think is fairly, I think it's a significant improvement on what's been done before. And I guess the thing I want to emphasize is that scattering is a fundamental limitation for VLBI. You can't get around it by building a bigger instrument or by improving sensitivity or anything like that. It's just like optical telescopes. You're limited fundamentally by the scattering. It's defining what you're actually observing on the sky. And so this is something where only algorithms can actually improve the performance of your instrument. So again, if you guys have interest in the EHT or statistical methods, please get in touch with us. I think there are a lot of interesting problems to think about, and thanks for your time.
Thank you very much. Very interesting. Questions? Vinay first.
I was just wondering, can you use the fact that there might be point sources nearby which could give you some sort of a interstellar PSF that you can deconvolve with?
It's a great idea. There's a magnetar very close by, which is effectively a point source. That can tell us the blurring part of the scattering. It's actually much too far away by a factor of about 10 to the 5 to use it for to mitigate these large-scale modes. So it's an interesting problem because that's the whole benefit of adaptive optics is you have a point source. Whereas here we have no point source, and that's why we rely on a statistical technique to infer what the scattering should be. But one interesting question is whether similar techniques could be used in the optical case and maybe relax the need for a bright point source nearby or laser guide stars or anything.
So I have a question to the technique. So in your approach, you have to assume the image, the image is actually being
The unscattered
out,
image, you mean?
the interesting image of the event horizon. I mean, if I instead of the image which we all think is there, if I have just the blob and do the scattering.
Yeah, so in these cases, I didn't tell the algorithms anything about what the unscattered image was. In these cases, it's actually just a flat prior. You do have to supply a prior, and in this case, it's basically saying it's favoring images that are smooth, it's favoring images that have a lot of entropy in them. But the technique is actually solving for that simultaneously with solving for the scattering. Yeah.
So if you're able to recover the image, what is the most important thing that you're looking for? What is the information that you most would like to recover?
Yeah, I think that there are a few layers there. The low-hanging fruit is this photon ring. And the reason that's so important is that it's almost independent of the spin of the black hole. It only varies by about plus or minus 4%, even if you go to maximal spin. And so this is a nice null hypothesis test of GR. We know how big it should be from the stellar orbits, and so we go out and we measure. If it's different than what we think it should be, that's an indication that GR is breaking down on these horizon scales. then you get into and the beautiful thing there is that's relatively insensitive to the astrophysics or the plasma physics. This is about the GR, about the lensing and the space-time near the black hole. The next layer is, studying the accretion physics and looking at, variability on these timescales, looking at variability basically on timescales of the ISCO, which for Sagittarius star is something like 30 minutes or less. And understanding the formation and launching of jets and all these other wonderful problems. But for us, I think goal number one is to look for a signature like the photon ring. Yeah.
We can have another question in the meantime.
Yeah.
Just a quick, it's a quick follow-up. So if you see this photon ring, how do you assess the significance of that? Whether it's detection or whether just the feature in your construction?
Well, that is a great question. That is one that I don't think that we have adequately addressed. And if you have ideas, it'd be great to hear them.
Thank you very much again. So we are moving to the next EHT speaker, that is Lindy Blackburn.
Hi, I'm Lindy Blackburn. I'm a postdoc with the EHT. I'm working largely on the data reduction and calibration side of the Event Horizon Telescope, and so I'm particularly interested in thinking about how we reduce our data and what sort of observables we really want to fit to. And I'll talk a little about the trade-offs between reducing and calibrating that data and interpreting it. So Michael gave a great introduction already, just to refresh what we're measuring really down here as correlations between signals recorded, essentially digitized and recorded onto disks, represents the correlated flux across the baseline in our array, and we can directly relate that to source structure on the sky. We're measuring Fourier coefficients of the source intensity profile. And the nice thing about our data here is that at least at a single telescope, our data is noise dominated, and all of those correlations we measure have independent errors. So you can imagine, just in this naive sense, the data fitting problem is rather simple. We can predict what we see in the telescopes, or at least in the correlations, and fit to independent data with independent errors. Now this becomes more complicated when you think about the sort of systematics that actually affect our measurements. So at the top here, representing what the correlated flux is, but then generically, as a signal propagates through, say, the atmosphere, through our instruments, it's subject to a certain number of distortions. And those distortions, the effect of those distortions are presented by some unknown complex gain in our system. So there's both, there's a complex gain, there's both some amplitude that we don't know. We don't really know the sensitivity of our detectors perfectly, and also some phase gain that's related to not knowing exactly the propagation delay from the source to our instruments. Now, so if you look at this, this equation, this means we have sort of an unknown gain for every measurement, and that's a non-starter. We're saved by a couple of properties. One is sort of this fundamental assumption that our gains are station-based. So that means they can be separated out into gain from station 1 and station 2. We have sort of order n squared pairwise measurements we make, and then sort of order n gains we're solving for. Another thing that can simplify this a lot is that, while the gains, might be a function of both time and of frequency, we're observing some narrow but still rather significant bandwidth in the data, maybe many gigahertz. And the gains are also time variable, which is very difficult to handle. They're usually separable in this sense, maybe with time variable gains being more environmentally influenced and frequency-dependent gains being things that are more like instrumental and electronics effects. So we rely on these sort of simplifications quite a bit when we do data calibration. And that's the reason sort of the whole thing's workable in the first place. Now, in classical calibration in radio interferometry, might follow something like this diagram here, where while we don't know the gains, we hope that we can use external measurements to measure them fairly accurately and then correct for them. So maybe we have a calibration source nearby to our source of interest that has known structure. We can look at that source with our array, solve for the gains, transfer them to our measurements, and then perfectly correct our measurements to get back, from our correlation coefficients, get back to measured correlated flux on the sky for a source. That doesn't quite work for the case of the EHT, which is 1 millimeter high frequency VLBI. For one thing, we don't have any calibration source with structure, known structure, at least at the resolutions we need. You know, we're measuring the smallest scales ever at this frequency, so we don't really know what any of the calibrators look like. So that, you know, that kills this plan here for solving for the gains. We have a very sparse array, which makes that, you know, reverse solution even more difficult, and just a number of problems, essentially making it very difficult for us to estimate the gains independently from the data itself. So that's a problem for this classical calibration approach. We can sort of estimate the gain, but essentially there'll be huge errors on there, and those huge errors will either bleed into our corrected data and introduce lots of covariant errors in that data, or just result in not very good fitting in the first place. And it really leads to, you know, a strategy where you might want to fit the source parameters and the calibration parameters at the same time. So that leads to a somewhat more modern approach, self-calibration, which is a standard procedure in interferometry calibration. So this is where you're trying to keep the data as its original data in terms of state of correlation coefficient with nicely behaved errors, and then fit both source model parameters and systematic parameters at the same time into that data. Now that's very close to what I think a modern way of data analysis looks like. It's a little complicated for us. One thing is that this is actually a very complicated system, and it's very hard from first principles to model this entire system. And the environment's very complicated, but then also the instruments are very complicated. There might be extra processing effects that aren't totally understood. So forward modeling the whole system is quite complicated. You know, if you do something like a maximum likelihood fit, you know, maybe the maximum likelihood point of all of your systematic parameters just doesn't fully explore the space sufficiently, and it might be very difficult to appropriately marginalize over those parameters as well. Hopefully, I'll get this back. Okay. So another approach is to use a trick in interferometry, which is sort of leveraging this idea here of the separability of the gains, or the factorizability of the gains into station-based quantities. That results in a number of things we call closure relationships across the array. So here I've drawn closed loops of 3 and 4 sites. And the first relationship is a closure phase relationship. So here you see the phase measured across baselines across 3 sites. And if you look at a closed loop and consider the direction, the phase is a vector quantity here. And if you think of a phase offset or sort of a arbitrary delay at one site, it'll subtract the phase from one baseline and add to the other. And if you add up the phase along this closed loop, the net effect is 0. So you're left with only source contributions to the phase in this closure phase quantity, which is a sum of 3 baseline phases across a triangle. Similarly, there's the same effect for closure amplitude. So amplitude being related to the sensitivity of each station. And the idea here is that you form a quotient of products of 2 baseline amplitudes where each station goes on the numerator and denominator of this quotient, and thus the station based sensitivities cancel out. So then your closure amplitude is also entirely determined from source structure and not your instrumental gains. So those are great. Of course, you pay something, right? You're losing degrees of freedom related to the unknown gains in each site. So this plot here represents the fractional amount of information you recover as your number of antennas increases. And you say from phases, you lose n-1 degrees of freedom, where n is the number of antennas, and n amplitudes you lose by forming these observables rather than the original baseline visibilities. So you do lose something, but you gain robustness to the gains themselves, which you can completely ignore as long as they're stable. However, if you count out, say, the number of triangles and number of quadrangles in an array, the scale is n cubed is n to the fourth, while the number of measurements is only scaling is n squared, right? That's the number of baselines. So obviously you overcounted pretty rapidly, right? By the time your number of sites increases, you get many more closure quantities than you have, independent data measurements actually present in your baseline measurements. So something happened, and what you really need to do is extract those unique degrees of freedom in your data, or you'll be overfitting dramatically or some other problem. So this one way of doing that is to sort of start, get some strategy to really extract the non-redundant sets of observables from these much larger sets of all the possible closure quantities you can construct. So this is a strategy that's well known for closure phases, which is you arrange your sites on a ring here. You pick one reference site, and then from triangles to that reference site, you can sort of add them together. When you get a vector here that cancels out another one, these phases will cancel out perfectly. You add these out, and you get you can construct an arbitrary triangle in your array this way. So if you just take what's highlighted in this small rectangle here as your set of closure triangles, you can actually form linear combinations of all these and form anything in the set. So you know that this contains all the information you need, and if you count them up, you get exactly the number of degrees of freedom you expect. There's a slightly more complicated strategy for amplitudes you can do. This represents a quotient of amplitudes, but if you select pairs of sites along this ring and just consider all the ways of forming these sorts of amplitudes, you can take products of those amplitudes and similarly form any kind of closure amplitude, count them up, and figure out that you've achieved the right number of degrees of freedom in this set as well. But there's one more problem that occurs here, just even taking those non-redundant sets, and that's that you've taken baseline measurements with independent noise, and you started adding them together in these ways, and this introduces covariant error in all those observables. So even if you go to the trouble of forming non-redundant sets, you still have covariance in your error terms that you need to properly account for when forming, say, a likelihood onto those observables. So as long as you can write that out, you can convert what your closure quantities with the covariant errors. You can convert that into a set of actually independent observables with independent errors. So that's nice. And another nice thing about being aware of the covariance of the errors is that in the case of, say, an arbitrary collection of baselines, like these constructions relied on almost at least a nearly full complete set of baselines. Otherwise, you might be missing connection pieces to form whatever closure quantity you wanted. But if you have the covariance matrix of errors on, say, an arbitrary set of baselines, you can use something like any kind of matrix reduction, like singular value decomposition, and extract the unique degrees of freedom that way, which is convenient in practice because we might be missing baselines for any number of reasons. So this is a really nice example by Andrew Shale. He's a graduate student in our group, using closure quantities to image. So instead of trying to fit directly to the visibilities, or in some sense, in this case, the amplitudes are fit using closure relationships. And so you can see this is one example from a paper he has in preparation where he's fit to visibilities, but there was a 25% amplitude error in the calibration mechanism. And that's about where, in this particular process, traditional fitting breaks down. On the other hand, fitting closure amplitudes is quite robust. So regardless of the calibration error, this doesn't care about it at all. We always see a very nice performance from the imagery construction. All right, so in summary, what we decide to do, what data we decide to fit to really depends on our situation. Right? In the classic calibration, this is great if you can independently estimate your systematic parameters, your gains, to high precision. And you just correct your data, you proceed as normally. Otherwise, it's very nice to fit to the raw data itself and put all of your model parameters into forward modeling. But because our system's so complicated, that's actually computationally quite difficult, and it's difficult to characterize the entire system and write a simulator to properly forward model everything. So in our case, we do have some tricks. We can use these closure relationships we lose the advantage of making use of this external gain information, but we do get a much more robust set of observations to fit to. And that's the end. Thank you.
Thank you very much. Questions?
How do you deal with, when you increase n, the number of stations you've got, the fact that the larger that number is, the more likely that they're all going to be suffering differing conditions? And at what point is increasing n a detractor rather than a detraction rather than an advantage?
If under these, say under, if you're looking at closure quantities, it's always an advantage. Or under self-calibration, it's always an advantage. You can always better fit your gains in self-calibration, and when you're considering closure, you always reconstruct a greater fraction of the underlying degrees of freedom with those closure quantities. It's certainly true that your whole system becomes very complicated, but I don't think I don't think that's intractable. I mean, I think
individual baselines would become increasingly uncertain because the conditions are more likely to be different local conditions. Doesn't that affect your ability to do closure in the first place?
we do run into a problem if we have very, very low signal-to-noise ratio on a baseline. It becomes difficult to evaluate errors in these either phase or amplitude, and thus closure phase or closure amplitude. But I think for the most part, we can either ignore those very low signal-to-noise ratio measurements, and in doing so, just use the observations we're confident about.
So in your self-calibrating model, have you tried running this, or is just the theoretical description of what you could do?
We do self-calibration, and the success of that really, I think, hinges on how well you can represent or how well you can characterize your priors and all the systematics. And right now, that characterization is rather simple, right? Maybe we assume that they change arbitrarily from each 5-second interval to another 5-second interval or something like that.
Yeah, because this is sort of a reminder for us about the way we treat the instrument uncertainties in forward fitting in spectral analysis. So we thought about the uncertainties on the instrument model, which for us was response matrix and effective error, and trying to characterize the uncertainty in those and then use them in the full forward fitting model where you actually have this uncertainty included there because you have a prior.
Absolutely, yeah. If we wanted to do
a measurement, and you can just do this self-consistently, and then you get the errors at the end on your parameters, for model parameters.
That's right, yeah. If we want to do the best possible job, we would have priors on all of our systematics, and we would explore that full space of systematic priors as we do our source fitting. But that's a very large computation.
I can imagine it's more things to actually parameterize more problem which we had about small the question how you go and sample the parameters.
Sure, yeah. And it's not just a computational problem. It's just attacked by many people. It's also just understanding our system, which we don't quite understand at that level of detail. So.
Let's thank Lindy again. And we're finishing the session with Katie Bowman, recently arrived at the CFA, right?
Yeah.
And this is going to be the last EHT related talk, right?
Yeah. Yeah, so, yeah. Thanks for inviting me to give a talk. I just arrived a couple weeks ago as a postdoc, but I've been working with the EHT during my PhD, where I was in the computer science department at MIT. So it's kind of cool to cross field, and it's neat to see all these different kinds of astrophysics problems. So in this work, I'm going to discuss a new method that we've been developing that allows us to reconstruct videos of time-varying radio sources at high resolution, like the EHT. And so as Michael and Lindy have mentioned, in order to take a picture of the black hole, the EHT has built this computational telescope that's the size of the Earth. And using this array of telescopes, as Michael said, it turns out that for every 2 telescopes in the array, we obtain a single measurement that tells us about the underlying 2D spatial frequency of the black hole structure. So that means, though, if you only had 6 telescopes, you would only sample at most 15 points, which is like an incredibly small number of points to try to make an image from. But as the Earth is rotating, we obtain other new measurements. So since the baselines between the telescopes change as the Earth rotates, this amounts to carving out different elliptical paths in the frequency plane. And this is what allows us to gather a lot more measurements that we can use to make a picture. And making an image really relies on the fact that we've observed the source over the entire night and we've carved out these different elliptical paths. So if we took just a single snapshot of measurements from a single time and tried to reconstruct a picture, there wouldn't be enough information to accurately represent the structure of the underlying image. There's just not enough data there. But if we observe the source as the Earth is rotating, we build up measurements, and slowly the structure of the underlying image will start to begin to appear. You're getting more information about different spatial frequencies, and so you're more confident also about the image that you reconstruct. And although most sources that VLBI techniques have looked at are static over the course of an observation, some sources, notably Sagittarius A star, which the EHT is really interested in, change on the time scale of just minutes. So here I show simulations done by Hotaka, who is a postdoc here at the CFA, and it's of Sagittarius A star at 2 orientations. And in this movie, every second corresponds to 3 minutes in real time. So that's incredibly fast motion. And here on the right, I show a bunch of these kind of data products like Lindy was talking about, like closure phase. And I show the comparison of when you just have a static source over the night versus a dynamic thing like this image. You see how much this data changes. And so that means that for a time-varying source, as the Earth is rotating, each measurement that we see is really collecting information about a different snapshot of the video. It's not, they don't all correspond to the same image. And therefore, if we try to reconstruct a picture, assuming that there is no motion and there is a single image that describes all the data, you'll get a result like this, where it's really, you can hardly see the primary structure. There's a lot of artifacts, and you really don't know exactly what's going on. So in response, and this is when you have a lot of motion, like this one on the left, but we've been trying to develop methods that reconstruct videos rather than single images. And therefore, not only can we maybe get a better image of the appearance, but we can also start to learn about the dynamics of what's going on, even though we only have a night of observation. So an initial idea you might have might just be, okay, well, you have different snapshots of data at different times, so you just independently reconstruct each image at every time. But like I said before, there's not enough information at every time, and so you really can't tell what's going on here. It's kind of nonsensical. So instead, we take a different approach. So this is what we do. We say, over the course of an observation, there are many different images that are observed. And for each of the images, we observe a different set of measurements. So each image is only associated with a couple different independent measurements. We have both sides of the frequency plane, but so that's why you have the closed red circles and the open circles. Those are kind of the same measurement information, but you only at one time might only have a couple different measurements. And so when you reconstruct, you get these very poor images like I showed. But however, by propagating information across time and sharing this information, perhaps we can do better. But the question remains, how should we propagate this information? Well, the first thing you might think about is you might say, okay, let's encourage each image to look similar to its neighbors. So over, the whole time, you might have a lot of motion and stuff, but from time to time, you might, the image of the source probably looks pretty similar. So if you constrain it to say, okay, I want it to look close to the images in time, then you can potentially share a lot of that information. But one additional question you might have is, how should we share that information? Should each pixel be treated equally? when we reconstruct an image, we are more confident about different parts of the region, different regions of the image we reconstruct. So maybe we should try to incorporate that uncertainty also in the propagation. And so how do we estimate this uncertainty? Well, we actually do it by estimating the full posterior distribution of each image. And so what do I mean by this? So I'm just going to take a step back, kind of to what a little bit like Michael talked about. So since we only have sparse measurements, then there are an infinite number of images that fit our measurements. So therefore, when we reconstruct images with EHT data, we do it by searching for an image that not only fits the observed measurements, but also scores well under some prior model. And this prior model tells us what we expect images to look like, and it does so by defining a distribution of what we expect the images to be sampled from. So it turns out that since we can describe the data likelihood as a Gaussian distribution, that if we also describe the image prior as a Gaussian distribution, then we can form a posterior that's also Gaussian and that we can easily solve for. So this posterior distribution provides all information about how likely each image is under the data provided that we see and the specified prior. And so what does it mean exactly to have this Gaussian prior distribution? Well, a multivariate Gaussian is specified by a mean image and a covariance. And the covariance tells us how each pixel is similar to every other pixel in the image. And by specifying the covariance in a certain way, you can kind of produce images with different types of structures. So you can define the covariance in terms of the image's power spectrum. And we can do that by specifying a parameter A, which I show here. And as A gets larger, it changes the covariance so that you produce smoother images. So here are some samples when I chose different A values. And you can see when you sample from this multivariate Gaussian distribution, you get smoother and smoother images. And so then we can then actually, taking a step back from the time variable imaging, let's just say we wanted to reconstruct a static image. So we could use this kind of multivariate Gaussian to reconstruct an image to decide between all of the images that kind of fit the data that we've measured. We can select which one is the most likely. And we get an image like, for instance, if this is the truth image, it was just a static image over the course of a night. Here are some other techniques that we've developed for EHT imaging with different kinds of priors. And here is one that we get when we use this kind of Gaussian prior. And you can see, although it's not as nice and sharp as the other ones, what we get for free is an estimate of our uncertainty in that image. So how much do we believe each pixel that we've reconstructed? And as we impose stronger and stronger priors by increasing the smoothness that we force, then we can also get different uncertainties. So as we make A larger, that means we imposed a smoother prior. So there's less uncertainty because we were very sure that we had this smooth image, even if that's wrong. But as you get more certain, then you can see what starts to come out is uncertainty just due to like what is in the data. So notice that you start to get this kind of elongation in this direction, which is caused due to you missing data in the frequency domain along that diagonal component. So using this allows us to not only reconstruct but understand our uncertainty. And then by propagating the reconstructed image and its uncertainty across time, we can obtain much better reconstructions that are often able to capture the true structure of the underlying source. So here I show some sample frames reconstructed, obtained using simulated data, assuming we use the same telescope array as we used this year in the EHT. But this is in the presence of no atmospheric corrupting noise like how Lindy talked about. However, even in the presence of this corrupting phase error, we're still able to recover this kind of ring nature, even with just the telescopes in the EHT 2017 array. The only difference here is that we have to use a nonlinear function, which makes the optimization a little bit tougher. But yeah, we still kind of improve results a lot over if you assume there's a static image. And here you can see the movie reconstructed from a single night of realistic data. when we assume that we have these phase errors. So similarly, here's a reconstruction you would obtain if the true underlying image is of an orbiting hotspot and you assumed it was just a static image. And here you can see the reconstruction when we reconstruct a movie rather than the static image. And you can start to begin to see the dynamics of the rotating spot. And even just adding a few more sites, it starts to become a bit more clear. Another thing we've explored is how to learn about the dynamics of the source without even imaging. So, if you have a source that is evolving in a similar manner over time, can we try to learn that evolution and understand the dynamics without even imaging directly from the data? So we approach this problem by turning the previous approach we take on its head, and instead of our goal being to reconstruct a video, we instead make an intermediate goal. We use the observations to find a function that connects the images. Particularly, we look at motion functions. And so we search for this motion function t that should approximately describe the transition between neighboring frames over time. However, with a typical way you would do this is you would actually require that you have the images, but we don't have the images. So how do we get around this? Well, just briefly, we use an algorithm that solves for this motion field, an expectation maximization algorithm that solves for the distribution of the latent images, these images that we don't see, but we try to estimate those distributions and then use that distribution to estimate the parameters of a motion model, a low-dimensional motion transformation. And so this allows us to solve for the direction of the underlying motion field using just those measurements without ever even seeing the underlying true movie. And then by plugging this transformation solution into the video reconstruction, we can go from a video like this one that really restricts the motion we're able to recover because we required that neighboring frames look very similar, to something like this that more accurately reflects the true dynamics of the video. And what's kind of neat is that in the case that you can't, that you don't even have a single motion field like this hotspot video, it's not the same motion field at all times, we're still able to recover the general direction of the motion. And so that means like this is just another approach to, without even imaging, we may be able to recover the dynamics of the targeted source from this VLBI EHT data. Thanks.
Thank you very much. Beautiful work. Questions?
Hey, so you mentioned that you're using this similarity of the images, consecutive images to make sure that to make the movie. I wasn't quite clear where in the process this information was put in.
Yeah.
Could you explain that?
Yeah, sure. So, we construct a kind of a optimization function that says, okay, I want each image. If I was to produce data from it under what we assume the system is like, it would look like the data that we've measured, and also that neighboring frames, the pixels in them, are very close in L2 sense we were using. So like the difference of neighboring pixels, the square difference of that is similar. The key, though, of the way that we propagate it through is that it's very similar to if you're familiar with like Kalman filtering, where you kind of propagate the information through by not only just saying what the, not just solving gradient descent and trying to say, I want to find the images that are very similar and fit the data, but also propagating the uncertainties in that. And so it would result in a closed form, forward-backward algorithm that is able to solve for the optimal images at every time using that method.
This is not the Bayesian algorithm that you mentioned, the one with the Gaussian reconstruction.
Yeah, so we use the Gaussian prior in that optimization. I just didn't discuss the details of it, but I'm happy to discuss with you offline. Yeah.
So, I think it's a nice idea to be looking at images that are, near each other in time to, use that as a constraint. But what happens when something surprising occurs? Which of course, I'm sure we're all hoping for, right? That there'll be things that happen when you're imaging
Like if
the
you have a
black
big
hole
flare or something like that.
Yeah, stuff that we never expected and that we'll learn a lot from. How do you make sure that you're sensitive to these changes, even if they turn out not to be huge and obvious?
Yeah, so one thing I'll say is that we have some sort of parameter in there that says how similar kind of neighboring frames should be. So even, despite us saying that we need frames to be very similar to each other, we're still able to do reconstructions like that hotspot video where, you have something that's a big bright spot that's kind of changing locations over the video. But yes, if you have some sort of big flare, it's probably going to try to, although something might show up, it might kind of mute it a little bit. So one thing you might do, though, is this is a way to just identify also what is kind of the structure of the source, which you might not be able to do with the typical the standard techniques we use for single image reconstruction. But once you learn what is the general structure, you can try to eliminate that from the data, and look for deviations from that to maybe pull out these kind of more unusual events. So yeah.
Trying different things. You won't just try one thing. You'll be.
Yeah, I mean, I'm assuming it will be an iterative process, but it's just without a lot of times I've found that without even allowing for the video to change, it's hard to get an initial kind of idea of what the structure is. So here is, I was just trying to show that you see how, even though we say neighboring frames should be similar, you have this hotspot that changes location. And so you do get like deviations over time. But as is shown in maybe this video, maybe the previous one, this one was assuming I didn't plug in some sort of idea of what the motion transformation is, and you see it kind of mutes the motion compared to the true video. It kind of constrains the motion, which is what you're saying. But if we try to learn this motion field, then you can try to pull it out. So maybe you could have a different kind of transformation or understanding of the over time as well.
More questions? I think we are done, and we have just. Yes, we are mildly late, but let's thank again all the speakers.
We should,
What time?
what time is it now?
3:30.
So we should, okay, how about
We have coffee. We have 10 minutes for coffee.
it's starting in 9 minutes?
This was great. Yeah. A lot of different methods. So yeah, we should actually get this. People talk more deeply.
Yeah. Good high-level teasers.
Yeah, it's very good.
Yeah, so I really would like to know the details.
Yeah, for sure.
Because, this is the kind of, were you here for the solar talks?
No, sorry.
Oh yeah. So we're online.
Yeah, no, but they have the same kind of issue, with things that are changing.
Changing it, yeah.
But only a little thing changes at a time. So, this process seems perfect for translating it somehow.
Yeah.
Positive.
I should talk to them to learn more. Like I said, I don't know too much about the. I've been taken under the wing of the EHT people. I don't know too much about it.
The thing with techniques is that you have a method can translate very easily to different fields and can produce very different astronomical results. So that can be very handy. So, yeah, we should talk.
Yeah, we should set up a.
At some point. And maybe the easiest way to do this is if you can give a talk at one of our AstroStat.
Yeah, for sure. Yeah, that would be great.
I'll send you an email.
Great, thank you very much.
I just want to say it was a fabulous talk.
Oh, thank
Very
you.
interesting. Did you give a talk at the BHI at some point recently?
It was
last year?
last year.
Okay, I think I saw that talk.
Yeah.
It looks like lots of wonderful progress has been made. I mean, I think that was a
I think
little
I
more
should
general.
have
but yeah.
it was at more early stages of that.
Yeah, as I was watching your talk, I was like, I think I've seen some of this before. But this is so much cooler now.
Thank you.
I assume Michael had to go on.
We actually have a board meeting really today.
Okay, well, run away. Thank you. Yeah, no, yeah, it's always really cool to see.
What's your name?
Anna Pancras.
Okay. You want to try to, is that the end of the meeting?
Yeah. Bye, guys.
Well, we are very late to the schedule. Try this. Hi.
Finally got a day. It's difficult to know what those parameters are. So I'm wondering, I do to London, like something more. Yeah, I said I had a flight more. Probably gonna postpone. I guess it's hard to know. Just like I had a flight on Sunday. But I can't figure out that. One thing that might cause me is like I'm in denial about that. You know, I have actual responsibilities. I'll just walk between them instead of around. Also, I have to have my mom took all my underclothes to moved out of my apartment. So I'm living in a backpack, and I only kept in my summer clothes. I'm not living in a backpack, it's living in an apartment. It was just a backpack of my summer clothes and this jumper. But turns out in Cambridge, UK, it's like this different. So I should probably get my office. So I just go to New York. No, you've seen my office. It's right behind me. Yeah, I threw out all the printouts of my own papers that I printed out to make myself feel more confident. When I'm writing a paper, I like to print out a draft every day, so I feel like it's a solid accomplishment. Why is that? Nice. I've done that too. Yes. In principle, you could. I have to think the framework allows. Yeah. So you see, do you know actually? Yeah. From down the hall. cleaning out my desk, I found the library.
What's happening?
Okay. He's just worried about the video. Yeah, okay. Which is not streaming. It is. Can we start in it? Give me a minute. Oh, wow. Because I think it's it's just not streaming.
Okay.
It's the streaming.
Yeah.
Because it was, somebody was saying that some part of was streaming and part of it was not. So.
Yeah.
Is this on? Yeah. Okay. So welcome to the last session of the day. We'll have 3 talks. Well, last part before the discussion, so don't leave after. Yeah. And so same with previous sessions, please feel free to interrupt and ask a question, but if you can, wait for the mic so that the feed can hear it. Okay, Arturo.
Yeah, thanks. Hi, my name is Arturo Avelino, and I'm going to talk about near-infrared Taiwanese supernova cosmology using near-infrared data. But in particular, I'm going to focus on describe a couple of tools that I'm using for doing this research that might be interesting for some of you. Probably some of you also know about these kind of tools. But first, let me give you a little bit of context of the problem. So supernova cosmology, the idea is to observe Taiwanese supernovae as standard candles to reconstruct the expansion history of the universe and then derive from that constraints of the dark energy. The nature of the dark energy is our ultimate goal used in all this analysis. But so far has been doing all this analysis, or the observational part has been using optical data. And there are problems with optical data because the light is dimmer and reddened from the dust, in the interstellar dust. And also the current samples, the optical samples are reaching or getting closer to the systematic errors versus systematic uncertainties versus the statistical uncertainties. So it means that adding more data, we are not going to get better constraints on dark energy. So one possibility to solve this problem is observing in near-infrared, where the universe is much more transparent at these wavelengths compared to the optical bands. And also, it turns out that the supernovae, the Taiwanese supernovae, are much more standard candles compared to opticals. So I have here some light curves from 2004 EY, where here are the optical bands, and these 4 are the near-infrared bands. So as you can see, they are different, slightly different between the opticals and the near-infrared. There is second peak and in the near-infrared, and they have their own properties. So the idea of using Taiwanese supernovae is derive distance modulus, or the relative distances from them, and then create a Hubble diagram from the supernovae when I have redshift versus the distance modulus. And from that, fit a a cosmological model to derive constraints on dark energy. For that, we need a low C sample of Taiwanese supernovae and a high redshift sample. This is for the optical bands, but we are working in the near-infrared bands, where the CFA has provided or observed a lot of supernovae, also the Carnegie Supernova Project, and now PanStar is getting data with very good resolution for the low redshift sample. And for the high redshift sample, we have a program also here at CFA, where Robert Kirchner, the principal, is the PI, called Raisins, where we are getting closer to the end of observing Taiwanese supernovae near infrared with the HST, and also with taking the optical counterpart from dark energy survey. And the coming W1st telescope is going to provide more data, more near-infrared photometric data of Taiwanese. So it's going to be very interesting to the future using this kind of observations for determining dark energy properties. So our ultimate goal is to get this a plot like this, where I have the modular density in the universe and the dark energy equation of state, and we want to derive some constraints using this combination between low C and high redshift sample of Taiwanese in infrared. Andy Friedman has compiled 154 supernovae from different sources, CFA, CSP, Chris-Unis, and we have a bunch of light curves like this, where here what I'm showing, all these points correspond to photometric light curves from J, H, and K bands, I mean near-infrared bands. And however, we don't have, we don't have a theoretical model that we don't completely understand the explosion of the Taiwanese supernovae. So we don't have a theoretical model that is reliable to describe the shape of the light curves in any given band. So we have to use a different approach to use this set of data series, of time series data, to infer distance modulus. And for that, in particular, I choose a non-parametric fitting method that is called Gaussian process regression that I'm going to describe in a moment. So, as I mentioned, the goal is to infer distance modulus from this near-infrared observation of Taiwanese. The method that we have developed in the group is essentially two steps. One is to construct a near-infrared template, or a typical template shape of the light curves in the different near-infrared bands. And the second step is use this template to feed the photometry and then infer the apparent magnitude at a given phase, at a given time. And for constructing the template, I'm using a couple of tools. That is where I want to focus more in the rest of the talk. Is the Gaussian process regression and a hierarchical Bayesian model. So the idea is, for the Gaussian process, is that you have a set of a data set. In this case, are the black points, and from that you can pass through these points a bunch of different curves or functions that fit the data, and this is shown in gray. But one of these, but the idea is to find what's the function that best fits the data that corresponds to the red one. So this is the key ingredients of the Gaussian process. So you have your data, and you have these random functions that correspond to the gray curves, and
And the Gaussian process corresponds to a generalization of having a Gaussian distribution, but now not for points, but for functions. So you have, instead of a point that is drawn from a Gaussian distribution, now you have a random function that is drawn from Gaussian distribution, where there's a mean function and a covariance function. In a typical standard simple Gaussian distribution, you have a mean standard deviation, so it's just a generalization, just with a notation that looks a little horrible, but the idea is very simple. And so you have your random functions, you have the data, so you draw samples you draw samples given the data and some times in the time series. This corresponds to the data, and you create a grid of points where you want to determine the value of the red curve. The red curve is going to correspond to the mean function. It's going to be the best function that fits the data. In this case, in red. So that's the main idea of this procedure. For our case and for the actual data, here I'm showing the light curve of T supernovae in the J band, and this is time in days. It's the cross-frame time of the supernovae. It is the prime magnitude. And what we have are the black points. And using the Gaussian process regression, what I get is the red curve, that corresponds to light curve, and also an estimation of the uncertainty in our knowledge of this red curve that interpolates the data. So obviously, where there is data with huge distances, the uncertainties is larger because the Gaussian process doesn't have enough knowledge to be precise enough in this region. But where there are more data, is you get a smaller covariance. So these are the key ingredients. So this random function. This random function is what you draw, and this is what you have as data. And what we want to obtain using the Gaussian process is the mean and the covariance that correspond to this. The graphical representation is in the light curve is these two parts that I have just explained. Here's a little more of the formulas. There's some already formulas to derive these quantities. Given this expression, I'm just going to skip. And here are some examples of fitting the light curves using the Gaussian process. It's the same supernovae at different bands, near-infrared bands. And from that, now the next step is to derive a template. And from that, I move to the second part, that is the hierarchical Bayesian model. It's a very simple hierarchical Bayesian model, where the idea of this thing is to ask the question of what's the typical light curve of the supernovae in a given band, for instance, Y band, given all the samples that they have, the samples that Andy Friedman has compiled. So I able to answer that question using this modelization of the problem. So I have one of the advantages of the hierarchical Bayesian models is that they borrow strengths between different elements of sample. So let me be very general. Now I'm going to specify a little bit more here. So you have a sample of whatever, and you want to determine the global or general properties from that, a general property or general parameter from that population. And you can use in just a simple average or a weighted average, or a step, additional step, it will be this hierarchical model. So I have all the light curves, and I ask what's the typical light curve. So here I'm going to derive, or I'm going to determine a new light curve for a given supernovae. S corresponds to a supernovae, so it's an index. And given all the data in the samples that I have, all the light curves in a given band that I have. So from that, I'm going to assume that they are normal distributed. So all the light curves that correspond, the new light curves that I'm going to determine, represented by this M, will be drawn from a mean light curve and the standard deviation. And this mean and standard deviation will correspond to the template, or to the mean light curve that comes from the population and its uncertainty. So let me show you what I get. These are the templates for Y and J band that I obtained. So let me show it for J band. Using all the light curves in J band from all the supernovae that I have, I obtained this black line that corresponds to the mean of in the population of the supernovae. Usually it is called the hyperparameter, and the standard deviation that corresponds to the green bar. Also, I obtained in both cases their corresponding uncertainty. So for the mean, this corresponds to the blue line. So the general, what I want to say is that using light curves and this very simple hierarchical model, I obtained these templates. So I can move to the final step of using these templates to feed the photometry and determine derive the distance model from that. So for instance, for J band, I have the photometry that this is the red dots, and I get the best fits of the templates to the red dot that is in green. And from that, what I want to derive is what the apparent magnitude at phase equals 0. Sorry for the axis. It should be time in days, and this is a apparent magnitude. Here we have. So my goal is make efforts to get a template is to fit to the data, and then infer what's the apparent magnitude at phase equals 0. Here I'm showing a couple examples. When there are data before phase equals 0 and after I could derive this value using actually the Gaussian process directly. In some other cases, when there is no data in that region, it's very helpful to have the template because I could infer these values. Using this method, there are some more additional steps that I have skipped, and I obtained this kind of Hubble diagrams for the low-C sample. Low-C, as you can see, is up to 0.04 redshift, and this is kind of the scatter that I get in the Hubble residual. I just want to finish with mention that the Gaussian process worked very well for our goal to interpolate the light curves when we don't have a functional form or a deep understanding of the explosion of the light curves. And this the hierarchical model that I use in it was very helpful for determining this template. I mean, to determine what's the typical or mean light curve of the supernovae and a given band. And this analysis is a much more simplified version of a full hierarchical Bayesian analysis that Casey Mandel has already done years ago. The idea is to have some intermediate analysis that is much more, is simpler, but know that, that we can derive good distance estimations of the supernovae. But yeah, well, I'm happy to answer questions.
So I wasn't quite clear. Do you always assume that you know the time of the peak well, or is that fit for as well, or?
Yeah, good question. In some cases, it's possible to infer the time the peak directly from the light curve. I mean, in the near-infrared band. I also have the optical bands. In practice, what I did is to use the optical band, B band, where we have theta in the at phase equals 0, or in the B maximum, and from that that has the reference time. Yeah.
I have one small technical question and then a more general one. So the technical thing, you showed the function, and then when you were saying, when you were trying to derive the true function given, or the set of possible functions given a sampled light curve, you had all of the possible functions going through the data points. So isn't there a likelihood that the true one could fall outside of those somewhat, because those are presumably 1 or 2 sigma uncertainties?
You mean the red?
Yeah, that's right. Yeah, couldn't you fall outside of that?
Yeah, in this case, I choose the very nice examples, but I get actually some cases where there's the red line, the point is here, and the curve is here. It tries to follow the thread.
That's all incorporated into it then. Thank you. Now, the other question had to do with comparing this method, which you're applying for the near-infrared light curves, to what people did historically for the optical light curves. So historically, there was kind of a conceptual flow, right? It was discovered by Phillips that there's a relationship between the peak magnitude and the decay time, and then little by little, people, found ways of characterizing how one type 1a supernova light curve differed from others, and so this range of light curves became so-called standardizable. Right. Now, in what you're doing, you're starting fresh, and you have a fully self-consistent method which would achieve the same thing. Is it? So I'm wondering, have you gone back and tried it on the optical light curves? Are you able to recover all of the power that people have found in the optical, or do you maybe even do better when you go back and do the optical light curves?
Yeah, actually, the answer would be the last part that you had said, that and is the ultimate goal of using this analysis, combine optical plus near-infrared. I'm just showing this for this word just near-infrared, but the idea is combined with the optical and combine power to get a more precise distance modulus from supernovae. And actually, Casey has already shown in his previous papers that it's possible that you get much better determination. Yeah, and just you mentioned that the light curves and the Phillips relation. It's interesting that I have found that the near-infrared are much more standard candles, or I have not found, because they have found what previous people, but I have just verified that they're standard candles, so I don't need to make these light curve corrections. That
So they're standard, not standardizable.
Yeah, exactly.
Interesting.
Okay, I think if there are no more questions, we're going to move on. Let's thank Arturo again.
we have the laser pointer? Did that go somewhere? The laser pointer?
Oh.
Oh, okay, sorry.
There's one here.
Thank you. I don't know where it went.
There's one here.
Oh, yes, I won't. I promise I won't steal it. Okay. Okay, perfect. I'm all set. Okay, hi everyone. My name is Katherine Zucker, and I'm a third-year graduate student here at the CFA. And today I'm very excited to talk to you about interactive, multidimensional data exploration and linking with Glue. And so Glue is a data visualization software. And I'm giving this talk on behalf of the Glue collaboration. So I'm an active Glue user, but I'm not actually a developer. And so most of that credit goes to others. The mastermind behind Glue is Alyssa Goodman. And then the lead developer of Glue is Tom Robitaille, with a lot of support from Chris Beaumont, Michelle Borkin, and Penny Kwan. And so the plan for today is I just want to basically set up the conceptual framework of Glue via a few slides. And then I want to spend most of the time giving a demo so you can see what Glue does and how you can implement Glue in your research. So we have Glue, and so Glue is a multidimensional data exploration tool. And so what does that actually mean? So it means that Glue supports linked views. And it supports linked views across your standard plots you'd want to make in any code that you write in. So you have standard 1D, 2D, and 3D plots. So things like scatter plots, histograms, or 3D volume renderings. But it also supports linked views from custom plots, so things like dendrograms or anything that you care to write a visualization viewer for. So all you need is a little bit of matplotlib code, but no GUI experience. And so I create a linked view by essentially highlighting live or algorithmic selections with Boolean logic. So I can essentially select one bar in a histogram, and then that'll automatically appear in the other viewers because they're linked, and we've told Glue how those different viewers relate to each other. And so once again, I can use my cursor, or I can use Boolean logic and say, basically, iteratively refine the subsets via and ors, and et cetera. And so Glue can not only do this with one data file, but it can do this across n data files. So you can look at multiple data sets at once with multiple file formats. So HDF5, FITS, ASCII, LaTeX tables, anything you probably use, Glue can support. And it can do this by essentially linking data file attributes. So basically, once again, telling Glue how the different data sets are related. And so this is all built in. So built in, we have our standard data loaders that allows you to integrate all these different file types. We have our standard 1D, 2D, and 3D plots. And then we have all these built-in features where we can define new variables. So basically create columns, new columns out of existing columns. We can import and export specific subsets of interest. We can, for instance, interact with things on the web, so via Jupyter Notebook or via online databases. And then we can actually save the state of our session and show it to someone else, and they can see exactly what you see in Glue. And so there's sort of the top level of Glue, and then there's a whole nother level that basically means that the possibilities are endless. So in addition to all the standard capabilities, you can actually iteratively refine your Glue environment via this customization. And so you have ability to make custom data loaders. So if you want to deal with Stokes cubes, for instance, which is a sort of a weird spectral cube with 4 dimensions, you can write a data importer that actually learns how to deal with that and integrate it into your Glue environments. You can create custom buttons and features. So Glue has a spectral tool. So you can actually extract spectrum from spectral cubes, but then if you wanted to, for instance, smooth that or sort of do another analysis on that spectrum, you can create a custom button or feature that will do that for you. And then once again, there's these custom plots. And so you have user set up input formats and user set up output formats that are both standard and things that you can do yourself. And on top of that, we have these additional options. So we have a config file that basically tells you how you want your environment set up. You can change the default colors and sort of the default plots that appear for you. You can actually access all of your GUI windows via a built-in IPython terminal and actually edit the visualizations in matplotlib, so basic matplotlib commands in Python. And then you can run and interact with Glue from Jupyter Notebook. And all of this is available online at glueviz.org and is open source. And so this is your Glue handout. So this is your quick introduction to Glue. And so I just want to briefly highlight which parts of glue are novel and which parts you basically will not find anywhere else. So the first thing that is very novel is linking data files with shared attributes. So why it's called glue, because you're gluing data sets together. Then you have this ability to make arbitrary 2D and 3D selections via your cursor and iteratively refine those selections. And then you can actually connect with Jupyter Notebook and send things back and forth between your Jupyter cells and your GUI. So now I want to get to the demo and how glue could be useful to you. And so I can launch glue very easily from my IPython terminal.
One question.
Yep.
How do I install it?
So there is a single, basically Conda install. Okay. So that's the favor. So you just, if you have a Conda environment, you can just install it in a single line. Yeah, so it's all online, but it's very easy to do.
It's Conda.
Yeah, Conda install Glubis. Conda install Glubis. And so this is basically your glue interface. There's a couple components. You have your data collection manager that stores all your data and all your subsets. And then you can tweak the visualization via these plot layers and plot options. And so I'm going to open a few different files. So I'm going to essentially open a catalog. I'm going to open a 2D image, and I'm going to open a 3D spectral cube. And so these are all the file formats that Glue supports, and so there's quite a few. And once again, if you don't have one that you want, you can make your own. So I'm going to import those, and then they'll appear in my data manager. And so the first thing we have to do with Glue is you have to tell Glue how these data sets are linked. And so we do this basically normally on just a one-to-one scale. So spatial coordinates are linked, kinematic velocities are linked. And so I can basically say that in this spectral cube, the latitude is linked in both, and the longitude is linked in both. And I can do the same thing between the cube and the catalog. So I'm going to say, once again, glon is equal to galactic longitude, glat is equal to galactic latitude, and then the velocities are actually also linked. So these are 3 data sets. And I'll get into what they mean in 1 second. And so if I actually want to visualize any of these data sets, I can drag it into my viewer. And so these are all the ones that are built in. So histograms, images, scatter plots, 3D volume renderings are all built in, but not all options will be available for all data sets. And so I can go ahead and make a 2D image. And so right now I'm showing you the distribution of column densities in the galactic plane for a filament called Nessie. And so see, it's this long filament feature right here. And via the plot layer window, I can actually iteratively find that view. And so not only can I look at that by itself, but I can actually overlay another data set on top of it. And so those are 2D scatter plots. And so those are actually very dense clumps of gas that form in the galactic plane, and they preferentially form along Nessie because of cylindrical fragmentation. So they're forming along this filament, and they'll go on to produce high mass stars. And so what I can actually do is I can tweak the visualization of these dense gas sources. So if I, for instance, want to look at the velocity of these sources on top of Nessie, I can color by, for instance, their VLSR, which is their velocity. Then I can do this. And so you can see they actually change colors. And so there's basically scatter points between -80 and -20. You can see actually all the ones along Nessie are the same color, which means they're the same velocity. And you have some other sources that are basically farther away that are probably local features. Not only can I color by an attribute, but I can also actually size by an attribute. So if I want to size, for instance, by the geometric radius in arc minutes, I can do that. And so I see, for instance, that this one, compared to this one, has a lot larger geometric radius. And so it allows me to color and size by 3rd and 4th attributes. So I don't even just have an image viewer. I can also do things like build a 1D histogram. So I'm showing the distribution of column densities in this image. And I can change my binning interactively. I can also do things like make a 3D scatter plot out of these same dense clumps of gas. And I can basically plot anything in this catalog versus anything else. So the possibilities are endless. And so I'm going to plot latitude and longitude and then distance. Oops, what did I do? There we go. So I'm going to set the bounds. And then I'm going to fix the stretch that I messed up. There we go. And so I can show data side limits. And so this is basically the longitude, latitude, and distance of these same clumps. And just like the 2D scatter plot, I can actually color by a different attribute. So for instance, by the peak temperature. I'm going to size it, but I can also color it. And the last thing I want to show is I can actually go ahead and make a 3D volume rendering of molecular gas around this filament. So this is CO gas, so it's tracing lower density gas. And so you can see here that this is showing the distribution of CO. I can change some of the parameters on here. So right here, if you zoom in, I'm basically seeing what the CO looks like in this region. So it's 3D volume rendering, which is very hard to get in other visualization software. And so I mentioned these subsets, which are basically the reason why glue exists. And so I'm going to create a subset to drill down into a region of interest, which is our filament, obviously. This is why I'm using glue. And so I'm going to create subsets manually on this 2D image. I'm just going to highlight the region around the filament. And so you see what happens is that because this image is linked to all 3 other viewers, I can see exactly which basically pixels in this column density histogram correspond to this region, this red region. I can see exactly which part of the spectral cube corresponds to the filament. So you can see this emission is corresponding to this filament. And then I can see the exact, basically, dense clumps of gas that are highlighted in this image. And so I can iteratively update it via the Boolean logic like I did before. And it'll automatically render in all viewers. So I just did the not mode, and so I iteratively refined my subset.
Can you do it in the opposite sense?
Yes. Yes. So for instance, if I want to change this, then it'll appear in my image. And so I can iteratively refine them in different regions. So it can be refined in any viewer as long as they're linked. Oh, I'm on not mode. That's why. There we go. Yeah, so I can do it in multiple cases. So I can iteratively find them in any viewer that I want. And so I also promised that I could use the IPython terminal. And so again, I control all of these things in IPython. And so if I type DC, this is my data collection manager, so I can basically look at all 3 data sets I have loaded. And then I can say, basically, I want the catalog. And I want, for instance, the 2D image. And so now maybe I want to create a very precise subset. So I want to know, basically, highlight a subset within a very specific longitude range and not just do it by hand. I can do that via the IPython terminal. So I can say, for instance, give it a label. I'm going to say fill long range. And then I can basically do some Boolean algebra. And I can say I'm going to say it's greater than 330 in longitude, but it's also less than 340. And so I can say DC, so that's my data collection manager, and I'm going to say new subset group. So I'm creating a new subset. I'm going to give it that label, and I'm going to give it my subset. And so now it's iteratively appearing in all of the plots. So this is what I just defined via Boolean logic. And so I just defined basically a subset that's greater than a galactic longitude of 330 and less than 340. And so I can do the same thing where I can create new components. So for instance, if I want to create a new component in my catalog. So right now, all my components are here. And so for instance, I have something called VLSR. That's in kilometers per second. Say I want something in meters per second. I can actually really easily create a new component and just do and then if I actually go and look at my scatter plot and I look at what attributes it has, it's now apparent. So I can basically, in real time, see exactly what I need and control it via either the GUI or the IPython terminal. And then the last thing I wanted to show is I can actually tweak all the visualizations in any of these plots, also in the IPython terminal. So I have access to all my viewers, so the image viewer, the histogram, 3D volume rendering, and the 3D scatter plot. And so if I want to edit the image viewer, I can just extract that from the applications viewer. And then I can grab the axes. And then just using normal matplotlib, maybe I want to give it a title. AstroStat glue demo, because I want everyone to know what the plot is. And then I can draw it. And then this becomes AstroStat glue demo, and so I can do anything I want, like adjust axes limits and so on and so forth. I can make the labels bigger. So even if I wanted to make something publication quality, I can actually go ahead and do that in Glue. And so I've done all this work for the last 10 minutes. And so what if I actually wanted to show someone this session where they would see all the linked views, they would see all these GUIs as they appear, and basically all the data would be there. So I can do that, and so I can not only import specific subsets like the green and red subsets, but I can actually also export the entire session. So I can say save session, I can say AstroStats Glue demo, and I can save it with data. So save. And then anyone who wants to see exactly what I'm doing, they can just do Glue and then AstroStats Glue demo. This will pop up, and so they don't have to know any Glue or any Python, but they know exactly what you're doing and how you did it. And so that's all I have right now. I'm hoping to save 5 minutes for questions. So if you want to see anything particular, feel free to ask. And thank you for your time.
So I like at the end you can kind of export your Glue session, but can you actually export any of the, is it actually being exported just as a Glue file, or can you actually export it as a Python file showing like your command log?
So yeah, so you can, for instance, if you want to save something as a subset as a NumPy file, and so you have basically an image and you want to save some mask in that image, or basically the pixel coordinates, you can easily, first of all, export it as a FITS mask, which can be written by Python, or you can write a custom data exporter in a few lines that it will export it as a NumPy file in whatever format that you like.
Okay, so when you're doing things in the GUI, is that actually creating, though, any kind of log in Python that you can export?
So you mean what you're typing into the GUI?
What you're, like when you're selecting an area,
Yeah,
say,
yeah,
is that
so-
something that you can export as not a Glue file?
Yeah, of course, yeah,
Okay.
definitely. So basically, let's go back to my iPython terminal. And so let's see.
Can you see your whole log?
So I can see all of my subsets. So I can access each subset, and then I can convert it to a mask.
Okay.
So for each data property, so if I wanted to do, so all of the subsets are stored, and you can easily export them as a mask. And so that's all saved in the Glue framework.
Okay, and can you export then? You did like the metadata crosswalk that you're doing between them. Is that something that you can export out independent of the whole Glue session?
So you want to export out the links, or what do you want to specifically export?
So you had to tell Glue how the data sets are linked. Is there a way that you can kind of export that like data dictionary?
Yes. So first, there's a couple of things you can do. You can do it on import or on outport. So basically, right now, I just sort of linked it manually because I wanted to show you how it's done. But in a few lines in Python, I can actually automatically load all those links and basically say beforehand, this equals this, this equals this.
Okay.
And then it'll already be linked. I don't have to do anything in the GUI, and it'll all be set up. And then I can do the same thing on output. Yeah, so basically anything that I do in the GUI, I can do 10 times faster in IPython with just a little bit of Python knowledge. Yeah, so none of it is sort of inherent to the Glue, the Glue session file.
Is it possible to make some statistics or analysis in Glue? I mean,
Yeah, so what do you want to do as a scientist?
for instance, just for the histogram to determine the skewness of the distribution or depth.
So once again, you'd have to write a custom button for that. So basically, Glue knows exactly what data is in each bin, and it keeps track of what subset you select. And so all you have to do is write a button that basically tells Glue how to fit something to a histogram, and it'll do it. So all you have to do is create a button where I just basically read in the data and the subset in sort of the Glue framework. I do normal NumPy commands, normal fitting, whichever you want to fit, to a histogram, and then it'll do that automatically. So that's sort of the reason that the customization is endless. So it's not built in here, but you can do it with just a few lines of Python and then have it built into your framework for the end of time. Yeah.
Is there any limitation in the size of the data that Glue can?
Yes, there definitely is. So the main bottleneck right now is if you have a 3D volume rendering, because it has to map on the fly, so from 3D to 2D or any other dimension. So if you have a large 3D cube, that's a problem. So if you go above a gigabyte or two, a few gigabytes, Glue starts to slow down. but we are actively aware of the need to sort of handle larger data sets, and so that's basically one of our main development priorities, is sort of get it into working with bigger data sets. But right now, I would say a couple gigabytes is sort of where it maxes out and then starts to give you the sad wheel face where it scrolls around. Yeah.
So I was wondering in terms of dealing with uncertainties. So it's really impressive the way it brings these images together. But sometimes, when you're using one data set versus another, there's some kind of an offset in the coordinates. And I have a specific example. Sometimes you're looking at cataloged stars, and in a small region, you may have many stars. Mm-hmm. And you're picking them up from 2MASS and Dennis and maybe 3 or 4 or 5 other catalogs, but they're all off from each other by, a half an arc second or an arc second. So if I tried to use glue to bring them together, is that possible, or would that be confusing, or would they just appear according to where they are in each catalog, and so I'd be double counting or triple counting sometimes?
Yeah, so all glue knows is what you give it in its WCS file. So if there's an offset in WCS, it won't understand that that's offset. So you'd have to correct before it via WCS. But one way we do deal with error bars, at least, is we actually can plot them in catalogs. So we actually have the ability to quantify errors in some of the viewers. So if I wanted to do like a 2D scatter plot, I can add error bars, which is, I know it's not exactly what you're asking because you want to cross-match catalogs, but I can quantify error bars, and so I can actually add things based on attributes. It's giving me. Correct, yeah. So you can actually, you know how I defined a subset in longitude? So I could basically define that in some radius around some point based on what you know about the error in the WCS. And so I could create tons of subsets of interest and basically quantify that again by your uncertainty in those regions. And so all of that is algorithmic. And so as long as you know the uncertainties and how you'd like to define the subsets, Glue can do them all in the IPython terminal.
A great thing would be if, when you put these together and you have them all in different filters and different magnitudes, if it were really smart, it could just say, okay, well, this has to be that star and this has to be that one, instead of leaving us still to do all that work, right?
Yeah.
Oh, yes.
But yeah, that is a good idea to be able to cross-match. So I know other sort of large databases that do that. So Glue doesn't have that currently built in, but I mean, if you're very savvy, you could easily write something, as long as you know a little bit of Python, that can basically correct for that when it's trying to make subsets. Yeah, so the limit is basically how well you can write Python code, not basically the software itself. Yep.
Okay, if there are no more questions, let's thank Catherine one more time.
We are a little bit delayed, but we'll have one last presentation from ADS group, and of course they will be talking about very different type of data. And after that, we hope to have a discussion. I don't know how many people will be in the room here for discussion. I know that there are people viewing us somewhere, so if they want to participate in the discussion and they are in the building, they may come back to this room, because it will be nice to actually finalize our thoughts about what we will do in the future. All right, so ADS presentation now.
Okay, is this on? Okay, thank you. So now for something different. I will talk about probably data that is quite unusual for an astronomer to deal with directly, because what ADS does is it indexes the literature, so a lot of what we deal with is text as opposed to numbers or pixels. And I will briefly give you a very quick overview of what data I think might be interesting for this crowd, and then let Mike Kurtz, who's the project scientist, talk specifically about one project that he worked on with a computer science graduate student regarding the analysis of ADS data. So what do we have in terms of what's the core database that we manage? We have 12 million records in ADS. Each record represents a scientific publication or something related to research artifacts such as data catalogs, observing proposals, even software records nowadays. So we have metadata concerning all of those 12 million records. We actually have the full text for not quite half of them, but for most of the articles in the refereed literature, we have the actual full text contents that we either extracted by digitizing the documents and then running optical character recognition on them, or by obtaining digital copies of the original documents, so they can be in different formats such as XML, PDF, or LaTeX. Using this information, then, we build citations that connect the records in our system. So we are able to say when a paper cites another one. And this creates a so-called graph, meaning you have papers which are represented by nodes in a network, and then you have connections which are the citations between them. So it's a directed graph, and you can build different graphs based on things such as co-authorship information or usage information. And speaking of usage, we collect in our logs anonymous usage data, so we know what papers are read more than others, and we also know how usage connects to papers. So someone who's read paper X has also read paper Y, and because people read papers not randomly, but for specific reasons, there are coherent paths that users create across papers. So this is another interesting data set. How we use them? Well, our new interface has some analytics and visualizations that leverage them. Here I just put a couple of them that show how you can create a scatter plot of papers generated from a search in ADS. And in the axis here, you see publication date in the first one versus read count, so the usage data in the 90 days for each paper, and the size of each record indicates how many citations it received. Or you can flip it and view citation count versus 90-day read count, with the publication date as the size of the dot. So this is just to show that when you connect those quantities together, you can then have some insights into any set of search results. You can also get insights when you leverage things such as co-authorship networks. You have people that collaborate together, so they're usually teams or groups within an institution, and then they write papers. So you can apply clustering algorithms to see who works with whom, and or you can do that over topics. So here, using the citation network, we can see clusters of topics related to how papers cite each other. So we assigned labels to a citation clustering network. Okay, so what are the challenges and what are the things that might be of interest for the crowd of astroinformatics and astrostatistics folks? We basically try to extract metadata and other attributes from scientific papers so that then we can present it to the users, and we can make most of the things that we extract easily searchable, and we can generate summary statistics from them. So there's, to the left is the first page of a paper, and to the right is the ADS record for this paper. So what have we done to create that record? Well, we have structured information. So the central information in this web page is the so-called basic metadata, which is paper title, the author list, the affiliations, the abstract, and so forth. But then we add let's say we add value to this first view of the descriptive view of the paper by mining content and enriching the record this way, collecting information from other sources, and then connecting information to this record. So in blue, I show the things that we obtain by mining the actual full text of the paper. We have thumbnails of the figures that appear in this AJ paper or AJ paper. We have citations, which are created by extracting references and analyzing what papers these references point to. And we have topics, so keywords that we extract from the paper. Right now, these are the ones displayed here as subject headings, but Michael will talk about how we can extract topics in an unsupervised fashion. What I here highlighted in red are links to external archives. So for instance, for a paper, you have links to the publisher full text or the archive version of the article itself. We have links to data which is hosted by other archives. So this is information that we collect from external sources. And finally, we have information that we collect ourselves, which is co-readership data, which is an attribute of the indicating, kind of the popularity or readership patterns for this particular paper that comes from our logs, and the metrics that we compute about each paper. How have we been doing this? As you can imagine, ADS has existed for about almost 25 years, so we've used different technologies as those technologies became available to us. So in the early days, and still now, for instance, the process of extracting strings from a list of references in a paper and then identifying the actual ADS records to create this citation network. It uses a lot of ad hoc extraction. So we maybe digitize the paper, or maybe we received an electronic document. We format it so that we try to identify the correct strings that correspond to each of the reference. And then we have some programs that, so here we show that there's some ugly code in between that tries to grab the correct data from the paper and then tries to resolve it, that is, find the corresponding ADS record in the system and output something like this, which gets automatically merged in our database so we can assign identifiers for each of the citation in the system. How would we like to do it? Is by using some of the more modern approaches to machine learning. In this case, I can show you how we envision doing this. If you see a paper, even without reading any of the text, you can probably identify which part of the page correspond to a particular bibliographic field. So the title is here in aqua, and the abstract is in yellow, the full text is in green, the affiliations and other labels are in blue. So if we could teach an algorithm to use the information that you gain based by looking at font size and location and content, then you could achieve the kind of result that right now we use all these heuristics to achieve. So what we plan to use, there's a product, an open source project called Grobid, which uses something called conditional random fields, which are models that are very popular when they're used to extract sequence modeling. So basically, it tries to evaluate the probability that a certain sequence of tokens represent a certain model. So this particular open source project tried to apply in different ways, conditional random fields to identify different parts of a document, and then within each part of the document, then to decompose further the parts of the what's in it. So as you can see, the so-called header information contains the author list, the affiliations. The full text will have the main body of the paper. The references will have individual citations. Each citation has further components to it. So we haven't started using this, but we know that it's being successfully used by the people who maintain the Simbad database, and we would like to later this year start training it on our data set and see if it provides these results. Michael, you would like to talk about our next project.
Oh, I would. Well, all right.
Yes. And put this on because they're taping it.
Okay. Let's see. There. Okay. Well, I'm going to talk about some of the machine learning stuff that, so you guys can look at it there, that we're doing. And anybody who wants to help do this, it's actually possible to have learning exercises that do some of this stuff. And it's not that difficult to get a published paper out of it in the informatics literature because it's pretty open. So the first thing I'll talk about is the machine learning algorithms that we're going to use, which are basically latent Dirichlet allocation, which can take a set of documents. We have about 1 million full-text documents in the recent physics literature in XML and easily parsable and all that. And that's what we usually take. I have a student, Christofsky, he's now a postdoc at Columbia, who did this already, so we know it can be done. He didn't do it using Spark, he'd used his own software. But now you would use Spark. You just sort of set it up. I could even do this. And what LDA does, latent Dirichlet allocation, is it takes the words in a document and it attempts to make word vectors out of them where they're actually not looking for vectors. These are probability simplexes, not vector spaces. But it's easier to think about them as vectors, and it actually works both ways. This used to be done with vectors and people creating the spaces, but now the spaces are created by Monte Carlo, techniques that, MCMC, Markov chain Monte Carlo, that will go and drop a word. You find a word in a document, you pick a vector that it could be from, and then you iterate on that with the weight, word weights to vectors and vector space weights to words until you have populated it. This works very well. You can, after the fact, go back and look at the words that are chosen to be with the highest probability associated with a vector or dimension, really, in the space, and they make sense. So you can assign topics, these are called topic models, to these vector dimensions in a high dimensional space. Normally you use a 500 or 1,000 or 2,000 dimensions to create the space, but when we've done it, the number of significant dimensions after you're finished is really on the order of 150. And you can name these. And we probably will do that, but not necessarily with what Christe's already done. We'll start using Spark and do it ourselves. Anyhow, a project which I think would be relatively easy to do is to take the astronomy literature and run it simply on the astronomy literature. We ran it on physics, geophysics, astronomy, everything we have pretty much. And that takes a few days on the cluster to do. I would imagine that Spark is substantially faster in that it's really set up, which what we did wasn't. I mean, we did it some years ago. I don't know why that stopped. Okay. I guess it'll come back on.
All right. The output would be a set of basically vectors in a vector space. They're formally probabilities of topics in a topic model space, which is a probability simplex. But the difference really is whether you use, say, Euclidean distances or Colbert-Liebert divergences as distances. We use the divergences and it works just fine, but you get the same answer if you pretend they're vectors and use normal vector space distances. Anyway, you can get those positions, and then you can get the distances from one object. Objects are papers, to all the others, or as many as you want, and that allows you to build a graph of topic similarity. And nope. There's, of course, good software to deal with graphs. Here's Spark's version. These are really quite fast and very powerful, which will allow you to deal with it. Having such a graph lets you see what topics, and here I don't mean topics in the topic model space, because you have now used that in order to get the distances. You can reevaluate that in terms of what topics are close to other topics in the idea space that you've created with the topic model. And that lets you build a map, an intellectual map of what is going on in astronomy if you do it with astronomy papers. Such maps have existed. This one was done by Bergstrom and Roswell, or Roswell and Bergstrom, almost 10 years ago for the entire space of scholarly publication using citations to get the distances between documents, and then clustering it using their algorithms. There are plenty of ways to do this. InfoMap is the algorithm that they use to do the mapping, and is, you can just get it on GitHub. So this would be an interesting thing to do, comparing a map done this way using citation or co-citation or one of those kind of measures with one that's created using the distance, intellectual distance in terms of subject matter would be very interesting. Any of these things are easily publishable, probably even in the astronomy literature, but certainly in the information science literature. Okay, I'm done. Ask questions.
I was just looking at this probability and statistics line, and it looks like there is no connection between this and astronomy at all.
Not large, no. No.
There's somewhere around.
Yeah, I mean, we just use applied probabilities statistics anyway. We're not big users. Yeah.
This is really fascinating. So you're using the way people cite the papers, or whoever did this for this particular.
Yeah. We actually have, this kind of stuff is automatic inside ADS now. Okay. Alberto showed one of those plots.
But now suppose, as we know, in many fields, even fields that, as Annette is pointing out, don't seem to be connected here to each other, in essence, people are doing very similar things. What's done in one field can often be mapped. Oh, thank you. So what's done in one field can often be mapped right into something that somebody does in another field, and then some graduate student or anybody comes along and says, well, I have to do something for my research, and you do it all over again. So if there were an intelligent way of actually identifying the conceptual and practical similarities, even though we don't
That's
know
what I'm
enough
proposing, of course. That's what I'm proposing that somebody do.
Well, how would you approach that? Because
first
people
you
might
would
use different words. They wouldn't necessarily use the same words.
No,
but
the
they
words
would
don't
mean
matter.
the same thing.
It's how they're used together. I mean, there has to be enough. But you can use this to do translation between different languages. It works fine. In fact, Christy and I have a paper coming out in JASIS about that. But it's not like that's a completely novel concept. The correlation of words with each other turns out to work So even if you don't know the difference between American and British spelling, all the American words and British words will occur in the same, with high probability in the same vector or topic, just because people use them in combination with other words that are used together with them. That turns out to work fine. That's been done now for, I don't know, the beginning of ADS was when I met Peter Osorio, and he wrote about this in the 60s. So it's, I don't think, yeah.
So two things. One, just on that, there's some interesting stuff with doing like distances and subtracting these vectors, and you can learn interesting words.
Yeah, word for that word's fine.
Like king. I think I forget what it is. Like
yeah,
woman plus queen equals.
Yeah, king plus man equals queen plus woman.
Yes. But the thing I really wanted to talk about was so on your sort of topic mapping stuff. Have you looked yet compared to sort of the thesaurus work to see whether the thesaurus is really picking out anything?
Yes, in fact, that's the point of the paper that Christina Alberto's the author on that. Have written. What we do is we have taken the documents and we have viewed the documents, the abstract of the document, and the set of keywords and thesaurus words to the documents as different translations of each other. And then we have looked for the point in that puts them all into the same vector space, or probability simplex. Then we have looked for the documents which we take the full text of the document as being the fiducial. And we take the distance in the space to the position of the same document in one of these other representations, either the abstract or the keywords or some other. Right? And we look to see whether it's the closest one or whether there are other different papers that are closer. And you can form a statistic for goodness that way. We've done that to the Unified Astronomy Thesaurus. When we did it, we discovered that it really wasn't very good in heliophysics and planetary physics. And that's now being corrected. But yes, in fact, it works very well. Yes?
Sorry, I don't have the mic, but...
Oh, well, while you're going around, I should say that two different fields doing the same thing. Latent Dirichlet allocation was invented first by somebody who was doing the evolution of genes. And second, completely independently, 4 years later, by somebody who was looking at text. And they used exactly the same methods, even the same words in the papers. And they're now both quoted, they're both cited about 25,000 times.
Well, I just wanted to know a little bit more about whether or not you considered using like cosine similarity. If you're already creating vectors in like a vector space model for the documents.
Yeah, it's Euclidean distance and cosine similarity are the same, except that you normalize the document to be on the surface of a unit sphere for cosine similarity. Yeah, sure.
Because I mean, there's also, I think it's it's term frequency versus document frequency. Like that's really common approach to this, and I just was wondering how it's.
Yeah, it works sort of. If you look at the plot that Alberto showed, let's see, let's go back. That one. That's how these get done. Just IDF on the titles.
Okay, I just wanted to like see where that was coming into play and how that differed a little bit more from what you were doing.
It's
very similar.
They're similar, but the creation of the vector spaces, essentially TF-IDF has a vector space model with 100,000 dimensions, which is every single word.
Yeah.
Whereas the real vector space models, and they've been going on since the 60s, have small dimensionalities.
Okay.
40, 100, 1,000.
Okay.
And that's the real difference. And they have different purposes.
Yeah.
The very high dimensionality ones, they actually work better for searching specific documents. whereas the low dimensionality ones work better for creating similar topics. So finding sets of documents.
Okay.
And that's how we use them.
Okay. And then I also just was a little curious with the topic mapping. Have you guys investigated neural networks at all yet? So for like the character by character probabilities for the terms?
Yeah, essentially that's what the real mechanism behind word to vec does.
Okay.
And we haven't, but you know about it.
Okay. Just kind of curious where you were with all of
Okay.
Anything else?
Are we done? Yeah, okay.
We're
All
done.
right, thank you.
Okay.
Thank you. Well, given the program, we have basically 5 minutes left for the discussion. Yeah, you have
We
questions?
can say a couple of things.
Yeah, we can say something. So I guess I give the microphone to you.
Well, I mean, people are obviously fading out, but some people have been hardy enough, and okay, so
Yes, wake up.
wake up. And of course, anyone who's been watching on the YouTube thingy machine in the CFA, please come over here now if you.
They are still alive.
The main reason that we did this was so people could kind of meet other people who are doing similar things in the CFA and sort of learn about what other people are doing and probably start collaborations to do things. And talking with various people through the day, I feel that part of that has been happening. But I'd like to hear about what you all think, and also what it is that you think we should be doing next. That is the main agenda for this discussion.
No, I can say something because I actually talked to a few people during the day, and the main question was whether we have to do the regular meetings and discussions, whether we want to have events like that a few times a year. And some people don't. Prefer to have the events like today at exact day because of the schedule, so you can plan ahead and know that would be the day they want to be here. Having regular schedule is often tricky because we are all busy and we know what happens after a while with the regular schedule. I should add that there was also a voice for tutorials, not tutorials actually. The question about sharing the information or about the tools we develop. So if Casey has his hierarchical model algorithm available somewhere on GitHub, so how do I know that he has this available for everybody? And sharing this information, whether we share it as a talk, as a presentation and tutorial. So somebody said, it would be great to have a Jupyter notebook and some type of tutorial going through. So, organizing those type of events. The library is a great place, actually, for the tutorials and events. And I know that Dana has been working on making it happen.
We have plans right now. I don't know if James wants to say a little bit about it. For a few different events talking about different algorithms and presentations.
Yeah, so let's see here. November, December, and January, we're planning one per month AstroStats sort of sessions. So the first one, the idea is we will solicit topics, ideas, things that people are interested in from the community, and then have that would be sort of like a tutorial using R, and then we'd use the examples during the tutorial to sort of teach some of these fundamental ideas specifically for astronomy when you're using statistics. And then the second half of that would be an open question and answer period with a statistician. So we have friends over in the statistics department at Harvard who are going to partner with us on that. And then the other two tutorials would be a little bit more in depth, talking about some specific tools or some comparisons between like Python and R for statistics, or the other one's stats. STEM. So another sort of statistics tool. But in addition to that, we're also organizing other events. So we have there used to be Code Coffee. We're trying to sort of bring that back at a certain point. So if you guys have ideas for stats or non-stats related events that would be opportunities for collaboration, us folks in the library are very much interested in sort of helping support that in whatever way that we can. And I'm sure actually Daylan, you have more as well.
In addition to that, we're also really interested in ways that we can help better curate and archive the code that you guys are actually writing. So the software, I know ADS, as mentioned, they have actually code that's now indexed in ADS, and we're interested in making sure you guys have the resources you need to actually publish and share your software. And so we're going to be doing like focus groups at AAS this winter. And hopefully in the spring we want to be able to have some sessions with you guys so you guys have the tools you need so you're getting the credit you deserve for the software you're writing. That's all I have to say, but all ideas welcome for what you might need.
Yeah, so I think on a related note, we were talking during the year about trying to have a kind of a regular group which would mirror in some sense what ITC does, but in this larger context of the data world and all the things that we do. So I think we probably need to come together and thrash out some ideas for that. But one thing which relates a little bit to what Dana was saying, and when you mentioned Casey's work, one of the things that we even do here is we keep, I'm sure we all reinvent the wheel, right? We're often doing things that somebody else here has done, either somebody's here now or they did it 5 years ago or even longer, right? Horrors, but people have done it already in some sense. But they didn't do it the way we did it or for our purpose. One thing that was going on at Cornell for a while, when there was the Shapiro-Tucholsky group in general relativity, is they made a kind of an institutional memory, which partly was the archiving and making sure the stuff was available, and partly it was making sure that there were people who knew how to do the things that the people who were leaving knew how to do. So it was kind of like going back to the old folkways, people who could train the ones who were there or coming up next to essentially take their place in some way and take the things that had been done and potentially make them better, use them and make them better. So that's one idea that I think fits in very well with some of the resources we're undoubtedly going to have to make us more effective. Because, today was great. I didn't get to come to all of it, but it's fascinating to find out what everybody's doing. But the question is, are we walking away with more expertise at the end? Well, in a sense, yes, because we know who to tap, if we have certain kinds of questions, right? But I think if we can do that regularly, and I would say, maybe it's regular days like this, but partly I think it's an informal thing where just those of you who don't participate regularly in ITC may not know they call it the senior group. I don't think we should do it the same way. But basically, those of us who are, they're real old. But those of us who really are interested in making these contacts and in making things happen, we could get together once every 2 months or so And instead of spending a day, we could spend a few hours, have lunch, discuss what's going on, maybe feature something that somebody has worked on, but to really make it an ongoing thing.
So, on that note, so you probably know, Roseanne, that we usually have every sort of twice a month we have talks at the Science Center with the statisticians. This year, all those talks are moving to the CFA, and so those talks can be a good venue for people to come and discuss.
Next one.
Yes.
Tuesday, next one.
Oh, yeah. Oh, sorry. Yes, I almost forgot. Yes, next one is Josh Spiegel is speaking next Tuesday in Pratt on nested sampling. Yeah.
So what time is it going to be this year?
1 o'clock. Wait, is it 1 o'clock or no?
I don't know. I think it's one.
I think it's 1
No,
o'clock.
one because we don't want to interfere with the seminar.
It's not 1 o'clock.
Halfway it conflicts with the planet lunch,
No,
and halfway
at 12, right?
it's at 12. But then at 1 is the Black Hole Initiative lunch.
Next week?
Every week.
Yes, they've been, yeah.
I'm
So
pretty
that's-
sure. I mean, we
that's the
should double
problem.
check, but I'm
That's the
pretty
problem,
sure.
right? Because we have
Every
too many
slot.
things
Well,
going on.
Tuesdays is a particular. Tuesdays and Thursdays are
So
horror
if
days.
people are really interested in methods, they will come to the talk, right? The talk is, like next week talk is about MCMC methods. So those people who are really into this, they will come to that talk, right? I mean, you have broad selection, so how do you deal with the competing things? It's your decision to make.
I mean,
I
the
guess.
CFA, there's a talk every half an hour. So you can't-
Yes, so one other comment. I should say that graduate students are organizing themselves very nicely, and they have their own journal club, so reading books and learning about statistics or machine learning, depends on the topic. Michael, who was here, Michael Johnson, suggested that we would organize a journal club on astrostatistics, which is maybe too much for some of us, but some people could actually benefit from this. So we have postdocs, I don't see them here, but they can organize themselves, right? So the question is what we as a community should do if we want to do. I mean, we all have to do our research. So, if somebody wants to find another person who is really going to help them, where do they come and how do they find those? I think Ireland is a good place to sort of communicate, especially now with the new furniture, which I didn't see.
Yeah, go sit on the chairs. Go bring them in.
I didn't want to say very much, just that when I first got here, I didn't even know that this existed. So I think one amazing change, especially if the talks are now going to be at the CFA, is to get all of the talks listed in the weekly emails so that people know that. And I think that would actually make a huge difference in terms of how many people come and attend. I'm really actually looking forward to the fact that they're going to be at the CFA, since I have not yet made it to any of them. And part of it, I will admit, was the motivation of walking to campus. Well, when there's so much else to do, so this is wonderful. Yay.
There's usually lunch.
I know there's lunch.
It's a good lunch. It's lunch because it's Chinese lunch or
Pizza, sandwiches.
Well, okay, I think we.
Any
comments?
Any other comments? Yes, because it's getting late.
Yeah, I think about the journal. So I wonder it could make sense to have some kind of journal, but actually to discuss problems that we have. And let me say, I have this problem. I don't have idea how to use this tool. Is there somebody in the community, the community that could help? I have a 1 hour discussion where everybody put ideas how to do that, and probably it could be helpful.
We need to have an email, mailing list.
Yeah.
Which would be, something like that, which would be the group where you can sort of exchange emails and maybe set up a time and people could meet together. So maybe that's a way to.
Maybe we should generalize it, call it math.
Well, something like that.
Or just help.
Help, yeah. No, I didn't go to say something.
Any more comments from people who didn't say anything? If not, then we close. And I think we will organize a next one next day, maybe in January, because what we saw was just the tip of an iceberg, and I think there are many more things happening in CFA, and we haven't seen those topics here, presented here, and I hope we will do that.
And maybe not for the whole day, because people fed out very quickly.
Yeah, and I can see that we overloaded the program.
Yeah, so maybe we can do afternoon or something like that.
Yeah.
So not in the morning.
If you have any ideas,
Just let us know. We'll be
Yeah.
happy to
help us too. Yeah, you can help. You can organize things. So, thanks.
Okay, thank you all.
Thank you, guys. I mean, this was really wonderful.